Our galaxy, like thousands others we have yet to discover, seems to have formed from nothing. Each one of these galaxies holds its own secrets and shares one big question: how did they come to existence? Join us as we explore the mysteries of the universe. The age of the universe is estimated to be approximately 13.8 billion years, a figure derived from a range of sophisticated observational data and theoretical models. This estimate is primarily based on the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, which provides a snapshot of the infant universe approximately 380,000 years after its inception. By studying the CMB and its subtle fluctuations, scientists can infer crucial parameters like the rate of expansion of the universe, known as the Hubble constant, which in turn helps pin down the universe's age. Another method involves observing the oldest known star clusters, particularly globular clusters, which contain some of the universe's oldest stars. By determining the ages of these stars through techniques like stellar nucleosynthesis, essentially examining the fusion processes that power stars, astronomers can set a minimum age for the universe. Additionally, the observation of the distribution and redshift of distant galaxies, as well as the intricate dance of cosmic structures governed by general relativity, all corroborate this 13.8 billion-year timeline. Through these interwoven scientific techniques and observations, we gain a coherent and remarkably precise understanding of the universe's age, revealing a cosmos that has been evolving and expanding for nearly 14 billion years. The Big Bang theory, which posits that the universe began as a hot, dense singularity roughly 13.8 billion years ago, is underpinned by several key pieces of evidence that together create a compelling narrative of cosmic origins. One of the most significant lines of evidence comes from the observation of the cosmic microwave background, CMB radiation. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow permeates the universe and is remarkably uniform in all directions, with tiny fluctuations that reflect the initial density variations from which galaxies eventually formed. The CMB is essentially the leftover heat from the Big Bang, now cooled to just a few degrees above absolute zero and serving as a snapshot of the universe when it was only 380,000 years old. Another cornerstone of support for the Big Bang theory is the observed expansion of the universe, first noted by Edwin Hubble in the late 1920s. Hubble's discovery that galaxies are receding from us at speeds proportional to their distances implies that the universe is expanding. This was a groundbreaking realization that suggested the universe was once compacted into a much smaller, hotter, and denser state. The abundance of light elements, such as hydrogen, helium, and lithium, also bolsters the Big Bang model. Predictions based on the theory neatly match observed concentrations of these elements, which were forged in the first few minutes after the Big Bang as the universe cooled and protons and neutrons began to combine in a process known as Big Bang nucleosynthesis. These lines of evidence, combined with large-scale structure observations and the success of theoretical models in predicting various cosmic phenomena, create a robust framework supporting the Big Bang theory. Each piece, from the CMB to the expansion of the universe and the distribution of light elements, interlocks to tell the story of a dynamic, evolving universe that began with a tremendous explosion of space and time itself. The cosmic microwave background, CMB radiation, is essentially the afterglow of the Big Bang, providing us with a snapshot of the universe when it was just a few 100,000 years old. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this faint microwave radiation permeates the universe and is remarkably uniform, with minor fluctuations that reveal the density variations present in the early cosmos. These fluctuations are the seeds that eventually grew into galaxies and cosmic structures we observe today. The CMB is a relic from a time when the universe transitioned from being opaque and hot to transparent and cooler, allowing photons to travel freely through space for the first time. The study of the CMB has yielded a wealth of information about the universe's history, composition, and structure. For instance, Measurements of the temperature fluctuations in the CMB have helped determine the geometry of the universe, indicating it is flat. The CMB has also provided insight into the proportions of dark matter and dark energy, essential components that influence the universe's fate. The detailed maps produced by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have fine-tuned our understanding of cosmological parameters, confirming predictions of the Big Bang theory with stunning precision. This radiation serves as a cosmic blueprint, offering invaluable clues that help us piece together the grand narrative of the universe's origins and its evolution over billions of years. The formation of the first atoms after the Big Bang is a fascinating journey that unfolded during a period known as recombination, approximately 380,000 years after the universe's inception. Initially, the universe was an extremely hot and dense broth of quarks, gluons, electrons, and photons. As it expanded, it cooled down, allowing quarks to coalesce into protons and neutrons within the first few minutes, a process known as Big Bang nucleosynthesis. These protons and neutrons then combined to form the nuclei of the lightest elements, primarily hydrogen, along with helium and trace amounts of lithium. However, at this early stage, the universe was still too hot for electrons to bind with these positively charged nuclei to form neutral atoms. Instead, it was a plasma where electrons and protons existed separately, scattering photons and rendering the universe opaque. As the universe continued to expand and cool, it eventually reached a critical temperature of about 3000 Kelvin, allowing protons to capture electrons and form neutral hydrogen atoms in a process called recombination. This transition had a profound effect. It decoupled matter from radiation, allowing photons to travel freely through space. These free photons make up the cosmic microwave background, CMB radiation that we observe today. With the formation of neutral atoms, the universe became transparent, marking the end of the Dark Ages and setting the stage for the formation of the first stars and galaxies. This profound phase change laid the groundwork for the complex and structured universe we see today, from the vast cosmic web of galaxies to the intricacies of planetary systems. The study of this epoch not only enriches our understanding of the universe's early stages, but also provides critical insights into the fundamental forces and particles that govern the cosmos. The large-scale structures of the universe are the grand, sprawling formations that define its cosmic architecture. These structures include galaxy clusters, superclusters, filaments, and voids, creating a vast and intricate cosmic web. At the heart of this web are galaxy clusters, which are massive groupings of hundreds to thousands of galaxies bound together by gravity. These clusters are often dominated by dark matter, making them gravitational beacons that play a crucial role in the dynamics of the cosmos. Galaxy clusters themselves are interconnected through even larger structures known as filaments. These filaments are vast strands of dark matter, gas, and galaxies stretching across millions of light years, forming the skeleton of the cosmic web. Between these filaments lie immense empty regions called voids, where very few galaxies reside. Superclusters represent some of the largest coherent structures and are conglomerates of galaxy clusters and groups. Our Milky Way, for instance, is part of the Local Group, which belongs to the Virgo supercluster, which in turn is part of an even larger structure called the Laniakea supercluster. The study of these large-scale structures provides essential information about the distribution and behavior of dark matter and dark energy. Observations reveal that these structures are not randomly distributed, but have evolved from tiny density fluctuations in the early universe, as evidenced by the cosmic microwave background radiation. Over billions of years, the interplay of gravitational forces caused these fluctuations to grow, resulting in the complex web observed today. This cosmic tapestry is not just a testament to the universe's vastness, but also a critical window into understanding its origins, composition, and ultimate fate. Cosmic voids, the vast empty regions punctuating the universe, form as a natural consequence of the gravitational evolution of matter in the cosmos. Initially, the universe was almost uniformly filled with matter, with slight density fluctuations present due to quantum perturbations in the early universe. Over time, these tiny fluctuations grew under the influence of gravity. Areas with slightly higher densities began to attract more matter, forming dense regions that would eventually become galaxies, clusters, and filaments. Conversely, regions with lower densities lost matter to their denser neighbors, gradually expanding and becoming more empty. As a result of this process, known as gravitational clustering, matter in the universe began to clump together, accentuating the density contrasts. Dense regions became denser, while low-density regions thinned out even further, leading to the formation of cosmic voids. These voids are not entirely empty, but contain very few galaxies compared to the surrounding filaments and clusters. The dynamics within voids are relatively quiescent since there's less gravitational tugging from neighboring structures, allowing them to expand more freely as the universe itself expands. The study of cosmic voids is critical for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. By examining the properties and behavior of voids, astronomers can gain insights into the overall geometry and expansion rate of the cosmos. Moreover, voids provide unique laboratories for studying the interplay between dark matter and baryonic matter, offering a clearer picture of the fundamental forces that shape the universe's large-scale structure. The observable universe is the portion of the entire cosmos that we can detect or observe from Earth, limited by the finite speed of light and the age of the universe. Light from the most distant objects we can see today has traveled approximately 13.8 billion years to reach us. However, due to the expansion of the universe, these objects are now much farther away than 13.8 billion light-years. In fact, calculations that account for the expanding space suggest that the radius of the observable universe is about 46 billion light-years. Astronomers measure the observable universe using a combination of techniques. One key method is the observation and analysis of the cosmic microwave background, CMB radiation. The CMB provides a snapshot of the early universe, allowing scientists to gauge the scale and uniformity of the cosmos at that time. By studying the CMB's fluctuations and using the principles of general relativity, cosmologists can estimate the universe's size, shape, and rate of expansion. Additionally, redshift measurements of distant galaxies play a crucial role. The redshift phenomenon, where light from distant galaxies is stretched to longer, redder wavelengths due to the universe's expansion, allows astronomers to determine how far these galaxies are from us and how fast they are receding. These observations, combined with detailed models of cosmic evolution, enable astronomers to map the observable universe and understand its large-scale structure. This gives us a profound view into the history and development of the cosmos, though it is important to note that the observable universe is just a portion of the whole universe, which could be vastly larger and even infinite. The limits of what we can observe are set by both the speed of light and the time that has elapsed since the Big Bang, providing a cosmic horizon beyond which we cannot yet see. Estimating the number of galaxies in the universe is a monumental task, involving a blend of observational data, statistical analysis, and advanced technology. One primary method involves detailed surveys conducted by powerful telescopes like the Hubble Space Telescope, which can peer deep into the cosmos and capture images of distant galaxies in small patches of the sky. One famous example is the Hubble Ultra Deep Field, an image that reveals thousands of galaxies within a minuscule fraction of the sky. By extrapolating these findings to cover the entire celestial sphere, astronomers can estimate the total number of galaxies. Another crucial tool is numerical simulations based on the cosmological principles and known distribution of matter in the universe. These simulations model the formation and evolution of galaxies over billions of years, providing estimates of their numbers and distributions. By comparing simulated data with actual observations, researchers can refine their estimates, accounting for galaxies that might be too faint or too distant to detect with current technologies. Currently, the most widely accepted estimate suggests that there are about 2 trillion galaxies within the observable universe. This number might seem staggering, but it represents just a visible fraction of the entire cosmological landscape. Future advancements in telescope technology, such as the upcoming James Webb Space Telescope, will undoubtedly refine these estimates further and could even reveal previously unseen galaxies, continuing to expand our understanding of the vast and intricate universe. The Hubble Deep Field HDF image is one of the most significant achievements in observational cosmology, providing profound insights into the early universe and galaxy formation. Captured in 1995 by the Hubble Space Telescope, this detailed image focused on a tiny, seemingly empty patch of the sky located in the Ursa Major constellation. Over the course of 10 consecutive days, the telescope compiled hundreds of long-exposure photographs to reveal thousands of galaxies, spanning a variety of shapes, sizes, and colors. Some of these galaxies are among the most distant objects ever observed, offering a glimpse into the universe as it was billions of years ago. The significance of the HDF image is manifold. Firstly, it provided compelling evidence that the universe is filled with galaxies, even in regions previously thought to be devoid of significant astronomical objects. This discovery helped to shift our understanding of the universe's vastness and richness. Secondly, the diversity of galaxies captured in the HDF, including spiral, elliptical, and irregular forms, has offered invaluable data on the evolution of galaxies over cosmic time. Observing such a deep field has allowed astronomers to study how galaxies change and merge, shedding light on the processes that have led to the formation of complex structures like the Milky Way. Moreover, the HDF has fueled further astronomical research and observation strategies. Its success led to subsequent deep field images, including the Hubble Ultra Deep Field, HUDF, and the Hubble Extreme Deep Field, XDF, each pushing the boundaries of how far back in time we can observe. These images collectively enhance our understanding of the universe's early stages, the behavior of dark matter and dark energy, and the overall marvel of cosmic evolution. The HDF has thus had a lasting impact on both observational and theoretical astrophysics, continuing to inspire discoveries and deepen our appreciation of the cosmos. The expansion of the universe is measured primarily through the observation of distant galaxies and the phenomenon known as redshift. Edwin Hubble's groundbreaking work in the 1920s laid the foundation for our understanding of cosmic expansion. Hubble observed that galaxies are moving away from us, and the farther they are, the faster they recede. This relationship is encapsulated in what's now known as Hubble's law. The primary tool for measuring this expansion is the redshift of light from distant galaxies. Due to the Doppler effect, light from galaxies moving away from us stretches to longer, redder wavelengths. By measuring this redshift, astronomers can determine the velocity at which a galaxy is receding. To quantify this expansion, astronomers use a variety of calibrated standard candles, astronomical objects with known intrinsic luminosities. The most notable of these are Type Ia supernovae, which have consistent peak brightness and serve as reliable distance indicators. By comparing the observed brightness of these supernovae to their known intrinsic brightness, scientists can calculate their distances. When these distances are combined with the redshift data, it becomes possible to construct the relationship between distance and recessional velocity. More recently, the cosmic microwave background, CMB radiation, has provided another tool for measuring the universe's expansion. By studying the CMB, particularly with data from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, cosmologists can infer various parameters that describe the expansion rate, known as the Hubble constant. Observations of the CMB's fluctuations allow for precise measurements of the universe's rate of expansion in its early stages, which can be compared with present-day measurements. These methods collectively give a coherent picture of the universe's expansion, revealing not only how fast the universe is expanding today, but also how this rate has changed over time. This data is crucial for understanding dark energy's role in accelerating cosmic expansion and provides key insights into the universe's past, present, and future dynamics. Dark matter is an enigmatic substance that constitutes approximately 27% of the universe, yet it remains unseen and undetectable by conventional instruments. Unlike ordinary matter, which interacts with light and can be observed through telescopes, dark matter does not emit, absorb, or reflect light. It reveals its presence through gravitational effects, warping the fabric of space-time around galaxies and galaxy clusters. This invisible scaffolding helps to explain why galaxies spin at such high speeds, without flying apart, and how large-scale structures in the universe have evolved over billions of years. Detecting dark matter is one of the most profound challenges in modern physics. Researchers employ a variety of methods ranging from observing cosmic phenomena to conducting intricate experiments deep underground. One approach involves looking for subtle gravitational interactions, such as the bending of light known as gravitational lensing, where massive objects like galaxy clusters distort the light from objects behind them. Another method involves direct detection attempts using highly sensitive detectors placed in mines or deep inside mountains to shield them from cosmic rays and other interferences. These detectors aim to observe rare interactions between dark matter particles and ordinary matter. Additionally, particle accelerators like the Large Hadron Collider search for signs of dark matter by smashing particles together at high energies, hoping to produce or detect dark matter particles. The quest to uncover the true nature of dark matter continues to be at the forefront of astrophysics and cosmology, holding the promise of unraveling some of the universe's most profound mysteries. Dark energy is a mysterious and pervasive force that comprises roughly 68% of the universe. Unlike dark matter, which binds galaxies together through gravity, dark energy is believed to drive the accelerated expansion of the cosmos. This concept emerged from observations in the late 1990s of distant supernovae, which revealed that the universe's expansion is not slowing down as once thought, but rather speeding up. To account for this unexpected acceleration, scientists hypothesized the existence of dark energy, a form of energy that permeates all of space and counteracts the attractive force of gravity on a cosmic scale. The influence of dark energy on the universe is profound and far-reaching. It affects the rate at which the universe expands, which has critical implications for its ultimate fate. If the current acceleration continues, dark energy could lead to a scenario known as the Big Freeze, where galaxies move so far apart that stars burn out and the cosmos becomes a cold, dark, and desolate place. Dark energy also impacts the formation and evolution of large-scale structures in the universe by working against gravitational collapse that leads to the creation of galaxies and clusters of galaxies. Moreover, dark energy may be linked to the cosmological constant, a term Einstein included in his equations of general relativity, which he later discarded as his biggest blunder. However, present-day cosmology suggests that this cosmological constant, representing a constant energy density filling space homogeneously, might indeed describe dark energy. The true nature and underlying mechanisms of dark energy remain one of the most compelling and elusive areas of research in cosmology, continuously pushing the boundaries of our understanding of the universe. The fate of the universe is a profound question that has intrigued scientists and philosophers alike for centuries. Based on current cosmological theories and observations, several scenarios could unfold, each dictated by the properties and behaviors of dark energy, dark matter, and the overall density of the universe. If dark energy continues to drive the accelerated expansion of the universe, a leading possibility is the Big Freeze, or heat death, where galaxies drift so far apart that star formation ceases, stars burn out, and the universe gradually fades to absolute darkness and near absolute zero temperatures. Another scenario, albeit less likely given current data, is the Big Rip. In this dramatic end, dark energy's repulsive force strengthens over time, eventually overpowering all other forces, tearing apart galaxies, stars, planets, and even the atomic fabric of matter itself. Alternatively, if the density of the universe were sufficient to eventually halt its expansion and reverse it, we might face a big crunch, where gravitational forces pull everything back together, culminating in a fiery, dense singularity. Each of these scenarios hinges on the nature of dark energy, which remains one of the greatest mysteries in cosmology. The ongoing quest to understand dark energy and its influence will ultimately help us unravel the destiny of our cosmos. Wormholes, as theoretical passages through space-time, capture the imagination with their exotic possibilities, from instant travel across vast cosmic distances to even theoretical time travel. Albert Einstein and Nathan Rosen first proposed the concept in 1935, combining the principles of general relativity to describe what are often termed Einstein-Rosen bridges. These hypothetical structures could create shortcuts joining two distinct points in space-time, potentially bending the laws of physics in mind-bending ways. However, the existence of wormholes remains speculative, as constructing or discovering one presents significant theoretical and practical challenges. For a wormhole to be traversable by humans or spacecraft, it would need to possess stability to prevent catastrophic collapse. This demands a form of exotic matter with negative energy density, a substance not yet identified in the observable universe. Such exotic matter would theoretically counteract the natural tendency of the wormhole's throat to pinch off and close. While certain quantum theories suggest that microscopic wormholes could exist at subatomic levels, any macroscopic counterparts are purely speculative at this point. Advanced mathematical models and extensive research into quantum gravity and other frontier sciences may one day provide more concrete insights. Until then, wormholes remain a tantalizing feature of science fiction and theoretical physics, showcasing the boundless possibilities birthed from the marriage of imagination and scientific inquiry. Black hole singularities represent one of the most extreme and enigmatic phenomena in the universe. At the very heart of a black hole lies the singularity, a point where matter is thought to be infinitely dense and gravitational forces become infinitely strong. This concept emerges from the equations of general relativity, which suggest that under certain conditions, the collapse of a massive star can continue indefinitely, compressing all its mass into an infinitely small space. At this point, the known laws of physics no longer provide clear answers, and the curvature of space-time becomes infinite. One of the most puzzling aspects of singularities is that they form a boundary of sorts, beyond which our current understanding of physics breaks down. Theories about singularities often lead into the realm of quantum gravity, where attempts are being made to reconcile general relativity with quantum mechanics. Physicists posit that to truly comprehend what occurs inside a singularity, a theory of quantum gravity is required, one that can account for the known forces at such extreme scales. Various hypotheses have been suggested, ranging from string theory's proposal of fundamental building blocks of the universe to loop quantum gravity, which reimagines space-time itself as a lattice of discrete chunks rather than a smooth continuum. The nature of black hole singularities continues to be a tantalizing mystery, setting the stage for future breakthroughs that may ultimately reveal the true workings of our universe at its most fundamental level. Studying the event horizon of a black hole, the boundary beyond which nothing can escape the gravitational pull, presents significant challenges, primarily because light itself cannot escape from within it. However, recent advancements in technology and methodology have allowed scientists to make remarkable progress in this area. One of the pivotal methods involves observing the behavior of matter and radiation as they approach the event horizon. For example, matter falling into a black hole forms an accretion disk, heating up and emitting intense electromagnetic radiation, particularly X-rays and gamma rays. By studying these emissions with telescopes and space observatories, scientists can infer properties about the event horizon and the black hole's immediate environment. A groundbreaking milestone in studying black holes came in April 2019, when the Event Horizon Telescope (EHT) collaboration unveiled the first-ever image of a black hole's event horizon. This was achieved by linking together a global network of radio telescopes to form an Earth-sized virtual telescope, granting unprecedented precision and resolution. By capturing and correlating the radio waves from the vicinity of the supermassive black hole in the galaxy M87, researchers were able to generate an image showing the shadow of the black hole against the glowing backdrop of hot gas and dust swirling around it. The EHT continues to observe black holes, providing crucial data that help refine theoretical models and deepen our understanding of these enigmatic cosmic objects. Such collaborative efforts exemplify the extraordinary lengths to which humanity goes to unravel the mysteries of the universe, using cutting-edge technology and international cooperation. Gamma-ray bursts, GRBs, are among the most powerful and luminous events in the universe, releasing in just a few seconds the same amount of energy the Sun will emit over its entire 10 billion-year lifespan. These intense flashes of gamma radiation are primarily classified into two types: long-duration GRBs and short-duration GRBs, each with different causes. Long-duration GRBs, which last more than 2 seconds, are thought to be caused by the collapse of massive stars, a process also known as a supernova or hypernova. When a star many times the mass of the Sun exhausts its nuclear fuel, its core collapses into a black hole or neutron star, while its outer layers are expelled in a massive explosion. During this collapse, jets of highly energetic particles are ejected at nearly the speed of light, emitting gamma rays as they interact with surrounding material. Short-duration GRBs, which last less than 2 seconds, are believed to result from the merger of two compact objects, such as neutron stars or a neutron star and a black hole. These collisions produce gravitational waves, detectable by observatories like LIGO and Virgo, and also release enormous amounts of energy in the form of gamma rays. The extreme magnetic and gravitational forces during these mergers generate conditions where gamma-ray photons are expelled at exceptional speeds, resulting in the bursts observed. The remarkable power of GRBs stems from the extraordinarily energetic processes that create them. The beaming effect, where jets of radiation are focused into narrow beams rather than being emitted isotropically, amplifies their apparent luminosity, making them detectable across vast cosmic distances. Studying gamma-ray bursts helps scientists understand the life cycles of stars, the formation of black holes and neutron stars, and the most extreme physical conditions in the universe. Ground-based and space-based observatories continue to monitor the sky for GRBs, contributing invaluable data to our understanding of these cataclysmic events. The concept of parallel universes, or the multiverse, is a tantalizing hypothesis, proposing that our universe might be just one of many coexisting within a broader cosmic landscape. This idea emerges from several lines of theoretical physics and cosmology. One significant source is the interpretation of quantum mechanics that suggests every event splits the universe into multiple branches, each representing different possible outcomes. Known as the many worlds interpretation, this theory implies that countless parallel universes exist where every conceivable variation of events and histories unfolds. Another compelling notion stems from the theory of cosmic inflation, which posits that a rapid expansion of space-time occurred moments after the Big Bang. Some models of inflation suggest that this process could create bubble universes within a vast multiversal structure. Each bubble could harbor its own unique laws of physics and constants, making them independent and potentially very different from our own universe. String theory also entertains the multiverse idea through its landscape of solutions, where different configurations of extra dimensions give rise to myriad possible universes within a higher dimensional framework. While these theoretical models are intriguing, direct evidence for parallel universes remains elusive. The multiverse hypothesis challenges our ability to test it empirically, as interaction between these universes would likely be limited or non-existent under known physical laws. Nevertheless, cosmologists and physicists continue to explore the implications of these theories, leveraging advanced mathematics, simulations, and astronomical observations. The quest to understand if parallel universes exist pushes the boundary of scientific inquiry, opening new vistas in our search to comprehend the full scope of reality. The search for extraterrestrial intelligence, SETI, represents one of humanity's most profound scientific endeavors, aimed at answering the age-old question, are we alone in the universe? SETI primarily focuses on detecting signals or signs of technology from distant civilizations. One prominent method involves scanning the sky with radio telescopes to identify unusual or structured radio signals. These signals, unlike the chaotic noise from natural celestial phenomena, would ideally exhibit characteristics of artificial origin, such as narrow bandwidths, repeating patterns, or pulses at specific frequencies. One of the flagship projects in this quest is the SETI Institute's ongoing effort, using facilities like the Allen Telescope Array in Northern California. This array comprises 42 individual radio dishes working together to survey vast swathes of the sky. SETI researchers carefully analyze incoming data, looking for anomalies that could signify intelligent life. In addition to radio waves, scientists have also expanded their search to include optical SETI, which involves detecting laser pulses or other forms of light-based communication that might be used by advanced civilizations. High-powered lasers could potentially transmit signals across interstellar distances, making them a viable medium for extraterrestrial communication. Beyond dedicated SETI projects, astronomers are also exploring exoplanets, planets orbiting stars outside our solar system. The discovery of thousands of exoplanets, particularly those in the habitable zone where liquid water could exist, has significantly boosted the potential sites for intelligent life. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, are identifying these worlds, offering targets for future studies. In combination with advancements in technology, such as more sensitive detectors and sophisticated data analysis algorithms, the likelihood of detecting extraterrestrial intelligence, if it exists, continues to grow. The search extends not only outwards into the cosmos, but also encourages reflection on our place in the universe and the possibility of civilizations sharing the vast expanse of space-time with us. The Fermi paradox, named after the physicist Enrico Fermi, encapsulates a profound and puzzling question in the search for extraterrestrial intelligence. Given the vastness of the universe and the high probability of many Earth-like planets existing, where is everybody? Despite the incredible number of stars and potentially habitable planets, we have yet to find any conclusive evidence of intelligent extraterrestrial civilizations. This apparent contradiction between the high likelihood of extraterrestrial life and the lack of observable evidence is what defines the Fermi paradox. Several hypotheses have been proposed to explain this paradox. One possibility is the rare Earth hypothesis, which suggests that the conditions required for life, particularly intelligent life, are exceedingly rare and specific, making Earth an exceptional case. Alternatively, the Great Filter theory posits that there are critical and improbable stages in the evolution of life, and that most civilizations never pass through all these stages. This filter could lie in our past, indicating we are extraordinarily fortunate, or in our future, suggesting that advanced civilizations might self-destruct or face insurmountable challenges. Other explanations include the idea that advanced civilizations are deliberately avoiding us or have ethical reasons for not contacting less advanced species, often termed the zoo hypothesis. Another intriguing possibility is that such civilizations communicate in ways we do not yet understand or are beyond our current technological capabilities to detect. It is also conceivable that intelligent life is so different from us that we fail to recognize it when we encounter its signs. While these hypotheses range from the pragmatic to the speculative, the Fermi paradox continues to drive scientific inquiry and philosophical debate, pushing us to explore further and refine our understanding of life in the cosmos. The theory of general relativity, formulated by Albert Einstein and published in 1915, revolutionized our understanding of gravity and the nature of space-time. Unlike Newtonian gravity, which describes gravity as a force between masses, general relativity posits that gravity is a result of the warping or curvature of space-time caused by mass and energy. Imagine space-time as a flexible fabric. When a massive object like the Sun sits on this fabric, it creates a dent, and other objects, like planets, move along the curves of this dent, which we perceive as gravitational attraction. Einstein's equations of general relativity describe this relationship mathematically, showing how matter and energy determine the curvature of spacetime, and conversely, how this curvature dictates the motion of matter and energy. One of the most famous predictions of general relativity is the bending of light by gravity, a phenomenon known as gravitational lensing. This was spectacularly confirmed during a solar eclipse in 1919 when astronomers observed the light from distant stars bending around the Sun as predicted by Einstein's theory. General relativity has fundamentally altered the way we understand the universe, enabling accurate predictions and explanations of various astronomical phenomena. It explains the precession of Mercury's orbit, the dynamics of binary pulsars, and the propagation of gravitational waves, which were first directly detected by the LIGO Observatory in 2015. The theory also underpins modern cosmology, influencing our understanding of black holes, the Big Bang, and the expansion of the universe. Despite its centennial age, general relativity remains a cornerstone of modern physics, continuously validated by experiments and observations, while also inviting new questions and deeper explorations into the fabric of reality. Quantum mechanics, the branch of physics dealing with the behavior of particles at the smallest scales, fundamentally governs the nature of atoms, subatomic particles, and their interactions. However, its implications stretch far beyond the microscopic realm, extending into the vastness of space and profoundly influencing our understanding of the universe. One of the primary ways quantum mechanics applies to space is through the concept of quantum fields. According to quantum field theory, every particle is an excitation of an underlying field that permeates the universe. These fields interact across space, giving rise to forces and particles that shape the cosmos. One striking application of quantum mechanics in space is Hawking radiation, proposed by Stephen Hawking in 1974. This theory suggests that black holes are not entirely black, but emit radiation due to quantum effects near their event horizons. Virtual particle pairs, which constantly pop in and out of existence in empty space, can straddle the event horizon. One particle falls into the black hole while the other escapes, making it appear as though the black hole is emitting radiation. Over immense timescales, this process can lead to the gradual evaporation of black holes. Quantum mechanics also plays a crucial role in the early universe, particularly in the formation and evolution of cosmic structure. The Heisenberg uncertainty principle, which states that one cannot precisely know both the position and momentum of a particle, leads to quantum fluctuations in the primordial universe. These tiny fluctuations in the density field expanded during cosmic inflation, seeding the large-scale structures we see today, such as galaxies and galaxy clusters. Moreover, the pursuit of a unifying theory such as quantum gravity seeks to reconcile quantum mechanics with general relativity, aiming to explain the behavior of space-time itself at the Planck scale, where quantum effects are significant. Quantum mechanics and its implications continue to reveal the deeply interconnected and intricate fabric of our universe, connecting the minutiae of the quantum world with the expanse of the cosmos. String theory is a sophisticated theoretical framework designed to reconcile the seemingly incompatible realms of quantum mechanics and general relativity. At its core, string theory proposes that the fundamental constituents of the universe are not point-like particles, as traditionally conceived, but rather tiny, vibrating strings. These one-dimensional strings can vibrate at different frequencies, with each specific mode of vibration corresponding to a different particle. For example, an electron and a photon would be different vibrational states of the same basic string. One of the remarkable features of string theory is its potential to unify all the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, into a single cohesive framework. This unification could lead to a theory of everything, offering a comprehensive description of the fundamental workings of the universe. To do so, string theory requires extra spatial dimensions beyond the familiar 3. Most versions of string theory posit the existence of 10 or even 11 dimensions. These additional dimensions are thought to be compactified or curled up so tightly that they remain undetectable at macroscopic scales, blending seamlessly into the fabric of our observable universe. String theory's implications extend beyond mere particle physics, reaching into the very structure and origin of the cosmos. It provides insights into the nature of black holes, suggesting that their most perplexing features, like singularities and event horizons, can be better understood through the lens of string dynamics. Additionally, string theory plays a significant role in cosmological models, potentially explaining the initial conditions of the universe and the inflationary period that followed the Big Bang. Concepts like brane cosmology arise from string theory, positing that our visible universe could be a 3-dimensional brane existing within a higher dimensional space-time. Although still largely theoretical and not yet empirically verified, string theory continues to be a fertile ground for research, offering novel angles to approach some of the most profound questions in science. By striving to bridge the microcosm of quantum particles with the macrocosm of cosmology, string theory enriches our quest to understand the fundamental essence of the universe. Studying the multiverse, a concept suggesting the existence of multiple, perhaps infinite, parallel universes, presents unique challenges, primarily because these universes may be fundamentally disconnected from our own. Nonetheless, scientists have developed several innovative approaches to explore this intriguing hypothesis. One of the main methods involves examining the theoretical frameworks that predict the existence of a multiverse. For instance, cosmic inflation, a rapid expansion phase just after the Big Bang, naturally leads to the idea of an ever-expanding fractal-like multiverse. Different regions of space could undergo inflation independently, creating bubble universes with their own distinct physical properties. Some scientists look for indirect evidence of the multiverse by studying the observable features of our universe. For example, certain anomalous patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, could imply interactions between our universe and others. These tiny temperature fluctuations hold clues about the conditions of the early universe and could potentially reveal inconsistencies that point to influences from other universes. Another avenue of exploration involves fine-tuning arguments. Some researchers argue that the precise constants and laws of physics that allow for life as we know it might be more easily explained if our universe is just one of many, each with its own set of parameters. In addition to empirical searches, advancements in particle physics and theoretical models offer essential insights. Experiments at particle accelerators like the Large Hadron Collider, LHC, might provide clues through high-energy collisions that could hint at extra dimensions or processes suggesting a multiversal architecture. String theory also supports the multiverse idea by proposing a landscape of possible solutions, each corresponding to a different universe with unique physical constants and laws. Sophisticated mathematical tools and simulations help physicists explore these complex models, offering theoretical underpinnings that can guide empirical investigations. While direct evidence of the multiverse remains elusive, these combined approaches, ranging from observational cosmology to high-energy physics and advanced mathematical theory, help scientists probe the profound and mysterious possibility that our universe might be just one of many in an unimaginably vast multiverse. This multidisciplinary pursuit continuously pushes the boundaries of human knowledge, challenging our understanding of existence itself. Imagine, if you will, the fabric of the universe as a calm, vast ocean. Now, picture a pebble being dropped into this ocean, creating ripples that travel outwards. These ripples are akin to gravitational waves, which are disturbances in the fabric of space-time itself. Gravitational waves were first predicted by Albert Einstein in his general theory of relativity in 1916. They are generated by cataclysmic events such as the collision of black holes, exploding stars, or the merging of neutron stars. When these massive bodies accelerate, they create waves that propagate through space at the speed of light. Detecting these waves is a monumental challenge that scientists have addressed with remarkable ingenuity. LIGO, short for Laser Interferometer Gravitational Wave Observatory, and its European counterpart Virgo are marvels of modern engineering. These observatories use laser interferometry to detect incredibly minute changes in distance. LIGO, for instance, measures changes as small as 1/10,000th the diameter of a proton. When a gravitational wave passes through Earth, it stretches and compresses space, altering the distance between mirrors in the detectors ever so slightly. By observing these minute changes, scientists can decipher invaluable information about the cosmic events that caused these ripples, providing new insights into the workings of the universe. The concept of space-time is a fascinating blend of dimensions that we have come to understand through the pioneering work of physicists like Albert Einstein. Imagine you are standing in a field and you have a map showing the north-south and east-west directions. These two dimensions help you navigate the terrain. Now consider time as an additional dimension, akin to how the hands of a clock tell you where you are at a particular moment in that field. Together, time and the three spatial dimensions, length, width, and height, form the four-dimensional fabric known as space-time. Einstein's revolutionary idea, presented in his theory of general relativity in 1915, was that massive objects like the Earth, the Sun, and even black holes warp this fabric of space-time. Imagine placing a bowling ball on a trampoline. The ball creates a depression, and if you were to roll a marble on that trampoline, it would spiral inward toward the bowling ball, much like how gravity works. This warping is what causes the motion of planets, the bending of light, and the intricate dance of galaxies. To help us understand and visualize these complex ideas, scientists often use models and computer simulations, making the abstract concept of space-time a bit more tangible and graspable for our human minds. The holographic principle is an intriguing concept in physics that suggests our entire universe might be akin to a vast, complex hologram. Imagine a traditional hologram, like the kind you might find on a credit card sticker, where a three-dimensional image is encoded on a two-dimensional surface. Now apply this idea to the universe. The principle posits that all the information contained within a volume of space can be described by information encoded on its boundary, much like a hologram. This radical idea emerged primarily from attempts to reconcile the theories of quantum mechanics and general relativity, particularly in the context of black holes. In the 1970s, physicist Stephen Hawking demonstrated that black holes emit radiation, which eventually leads to their evaporation. This raised a perplexing question. What happens to the information that falls into a black hole? Jacob Bekenstein and later Leonard Susskind and Gerard T. Hooft proposed that this information isn't lost but rather encoded on the event horizon, the black hole's surface area. Extending this concept further, the holographic principle suggests that the whole universe can be thought of in similar terms. Research in theoretical physics continues to explore this principle, especially within the framework of string theory and quantum gravity. While still largely speculative and not yet confirmed by empirical data, the holographic principle offers a tantalizing glimpse into a potential unification of the fundamental forces of nature and helps us ponder whether our perception of reality might be vastly more complex and simpler than it seems. Simulating the universe inside a computer is a task that requires immense computational power, intricate algorithms, and a deep understanding of the physical laws governing the cosmos. These simulations start with the fundamental principles of physics, encapsulating everything from gravity and electromagnetism to complex fluid dynamics and quantum mechanics. Scientists input initial conditions, such as the distribution of dark matter and gas in the early universe, and then let the simulation evolve according to these laws. One of the most famous and extensive simulations is the Illustris project, which models the evolution of the universe from just a few million years after the Big Bang to the present day. This simulation involves billions of particles representing dark matter, stars, gas, and other cosmic phenomena, calculating their interactions over billions of years. Computational astrophysicists use powerful supercomputers, each capable of performing trillions of calculations per second, to handle these simulations. Techniques like adaptive mesh refinement are employed to focus computational resources on areas of interest, such as the formation of galaxies or the intricate structures of cosmic webs. These simulations are not just high-tech eye candy, they are tools for testing theories about the universe. By comparing the simulated data with actual astronomical observations, scientists can validate their models or refine them to better fit what we see. This iterative process helps us understand how galaxies form, how dark matter influences cosmic structures, and even phenomena like supernovae and black hole mergers. These digital universes offer a sandbox for scientists to explore the evolution of the cosmos in ways that are impossible through observation alone, pushing the boundaries of our understanding of the universe. The Higgs boson, often referred to as the God particle, holds a pivotal place in our understanding of the universe. Named after physicist Peter Higgs, who along with others proposed its existence in the 1960s, the Higgs boson is unique because it is associated with the Higgs field. This field permeates the entire universe and is responsible for giving mass to elementary particles. Without the Higgs field, particles like quarks and electrons would remain massless, making the formation of atoms, and consequently matter as we know it, impossible. In 2012, the existence of the Higgs boson was confirmed by the scientists at CERN using the Large Hadron Collider. Imagine the LHC as a colossal racetrack where protons zip around at speeds nearing that of light, eventually smashing into each other. These high-energy collisions produce a burst of particles, one of which is the elusive Higgs boson. Detecting the Higgs was no small feat. It decays almost instantaneously into other particles. By analyzing the debris from these collisions, scientists were able to identify the signature of the Higgs boson, confirming a cornerstone of the standard model of particle physics. The discovery of the Higgs boson is monumental because it validates decades of theoretical work and helps explain a fundamental aspect of reality. why some particles have mass and others don't. Moreover, it opens new avenues for exploring physics beyond the standard model. Researchers continue to study the properties of the Higgs boson, looking for any deviations from predictions that could hint at new physics, such as supersymmetry or other dimensions. The Higgs boson is not just another particle. It is a gateway to deeper understanding and potentially groundbreaking discoveries in the world of physics. The anthropic principle is a fascinating and somewhat philosophical concept that touches the very essence of why the universe appears the way it does and how it relates to life, particularly human life. In the realm of cosmology, the anthropic principle essentially posits that the universe's fundamental parameters are as they are because they allow for the existence of observers like us. There are two main versions of the principle: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle states that the observable universe's properties must be compatible with the existence of life. Otherwise, we wouldn't be here to observe it. Think of it this way. If the fundamental constants of physics, such as the gravitational constant or the charge of an electron, were even slightly different, the universe might not have formed stars, planets, or life. This view doesn't make a claim about why the constants are what they are. It merely notes that their observed values are conditions necessary for our existence. On the other hand, the strong anthropic principle goes a step further and suggests that the universe must have properties that inevitably lead to the emergence of conscious observers. This version often leans more into the realms of metaphysics, suggesting that the universe is somehow compelled by necessity or design to allow for the existence of observers. It's a more controversial stance and raises intriguing questions about purpose or design in the cosmos. Both forms of the anthropic principle have ignited considerable debate and introspection among cosmologists and philosophers. They serve as a reminder of the delicate balance of physical laws and constants that make our universe hospitable to life. While some scientists use the principle as a heuristic tool to explain why the universe has the properties it does, others critique it for not being empirically testable or for veering too close to tautology. Nevertheless, the anthropic principle remains a thought-provoking aspect of contemporary cosmological discourse, encouraging us to ponder not just the how, but also the why of our existence in the grand cosmic tapestry. The conditions necessary for life to exist, at least as we understand it, are quite specific and intricate. Firstly, liquid water is often considered the essential solvent for biochemical reactions. Water facilitates the transport of nutrients and waste products, aids in temperature regulation, and plays a pivotal role in cellular processes. This is why the search for extraterrestrial life often starts with the hunt for water in places like Mars or the icy moons of Jupiter and Saturn. Secondly, a stable source of energy is paramount. For life on Earth, the sun is the primary energy source, driving photosynthesis in plants and regulating climates. However, other potential energy sources, such as geothermal vents on the ocean floor or chemical reactions, could also sustain life. The energy must be harnessable in a form that organisms can convert into the biochemical processes that sustain them. Another crucial condition is the presence of essential chemical elements, often dubbed the building blocks of life. These include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon is particularly special due to its ability to form complex and stable bonds with many other elements, making it the backbone of organic molecules like proteins, lipids, nucleic acids, and carbohydrates. Additionally, a hospitable environment with moderate temperatures and atmosphere is crucial. Extremes in temperature can denature proteins and nucleic acids, whereas a stable atmosphere can provide protection against harmful radiation and facilitate the exchange of gases like oxygen and carbon dioxide, which are critical for respiratory and photosynthetic processes. Finally, time is an often overlooked but vital condition. Life, especially complex life, doesn't form instantaneously. It requires extensive periods for evolution, from simple molecular interactions to the development of complex multicellular organisms. This process can take billions of years and is influenced by a planet's stability over time, including factors like tectonics, magnetic fields, and the absence of cataclysmic events. The conditions necessary for life to blossom involve a delicate balance of available liquid water, energy sources, essential chemical elements, a conducive environment, and ample time for evolutionary processes. These criteria set the stage for the natural processes that could one day generate life, whether on Earth or potentially on distant worlds. Extremophiles, organisms that thrive in extreme environments on Earth, offer a fascinating window into the possibilities of alien life. These resilient forms of life can endure conditions once thought to be completely inhospitable. For instance, thermophiles can survive in boiling hot springs, while psychrophiles flourish in the freezing waters of the Arctic and Antarctic. Acidophiles thrive in highly acidic environments like those found in sulfuric hot springs, and halophiles prosper in extremely salty conditions, such as those of salt flats and saline lagoons. These organisms challenge our conception of the boundaries for life, expanding the range of environments where we might expect to find extraterrestrial life. Take, for instance, tardigrades, also known as water bears. These tiny, nearly indestructible creatures can endure the vacuum and radiation of outer space, extreme temperatures and high pressures. Their resilience suggests that life, if it exists elsewhere, might not be confined to Earth-like conditions. Another remarkable example is the discovery of microbial life miles beneath Earth's surface in rock formations, illuminating the possibility that life could persist in similar subsurface environments on other planets or moons. The study of extremophiles thus informs the search for life on other planets and moons. The icy moons Europa and Enceladus, which have subsurface oceans beneath their frozen crusts, are prime candidates for harboring life. The presence of hydrothermal vents on these ocean floors could provide the necessary heat and minerals, much like the vents on Earth where extremophiles thrive. Mars, with its evidence of past liquid water and present subsurface ice, is another focal point, especially in regions with perchlorates where halophiles might potentially survive. By studying extremophiles, scientists can better design missions and instruments to detect life in extreme conditions beyond Earth. For instance, NASA's Perseverance rover on Mars aims to collect samples that may contain signs of ancient microbial life, searching in places analogous to Earth's hydrothermal environments. Instruments are designed to detect specific biosignatures, informed by what we know about extremophiles. Extremophiles serve as Earth's gritty ambassadors in the quest to understand life's potential beyond our planet. They demonstrate that life can adapt to a myriad of extreme conditions, broadening the horizons for astrobiology and offering valuable insights into where and how we might find signs of life elsewhere in the cosmos. Detecting life on other planets involves identifying key indicators or biosignatures that strongly suggest biological activity. The primary focus is on finding chemical, physical, and sometimes even geological markers that either directly or indirectly point to the presence of life. These indicators vary from the atmospheric composition of a planet to surface features detectable through telescopes and space missions. One of the most crucial biosignatures is the presence of specific gases in a planet's atmosphere that are often associated with biological processes. Oxygen, for example, is a strong indicator because it is highly reactive and depletes rapidly without continuous replenishment. On Earth, this comes from photosynthesis. Methane is another significant gas since it can be produced by microbial life. When found together, oxygen and methane could be particularly telling because they react with each other, mutually depleting their concentrations unless replenished by some processes, suggesting a dynamic balance likely maintained by life. Another key indicator is the presence of liquid water. As a universal solvent, water facilitates most known biochemical reactions. Many mission designs, like those involving Mars rovers or Europa landers, focus on finding signs of liquid water or its past presence. Features such as river valleys, lake beds, or the spectral signatures of hydrated minerals hint at the history of water and its potential to harbor life. Surface features and geological formations also play a critical role. For instance, stromatolites, layered structures created by microbial communities on Earth, provide direct evidence of microbial life. Finding analogous structures on other planets or moons might suggest similar life forms. Additionally, fluctuations in the reflection spectrum of a planet's surface indicating vegetation or other biological activity, are scrutinized by telescopic observations. Organic molecules, complex carbon-based compounds, are another promising indicator. Missions like the Mars Curiosity rover have found tantalizing hints of complex organic molecules in Martian soil. While not definitive proof, the presence of these compounds can point to prebiotic chemistry or even active biological processes. Technosignatures, or signs of advanced technological civilizations, represent another fascinating aspect. These could include unusual patterns of light that might indicate artificial structures or waste heat detected through infrared telescopes, suggesting large-scale energy use. Radio signals or other forms of communication could also be indicators, which initiatives like SETI, Search for Extraterrestrial Intelligence, aim to detect. Key indicators of life on other planets span a range of evidence, from specific atmospheric gases and liquid water to geological formations and organic molecules. Each of these clues helps build a compelling case for the potential presence of life, guiding the design and focus of space missions as humanity continues the quest to discover whether we are alone in the universe. The search for biosignatures on exoplanets is a multifaceted endeavor that relies on advanced technology, intricate methodologies, and a deep understanding of both astrophysics and biology. The primary tools for this quest are powerful telescopes, both ground-based and space-based, equipped with sophisticated instruments capable of analyzing the light from distant celestial objects. Through a combination of techniques like spectroscopy, direct imaging, and transit observations, scientists aim to detect signs that might indicate the presence of life. Spectroscopy is among the most crucial techniques used in this search. When a planet passes in front of its host star, starlight filters through the planet's atmosphere, and molecules in the atmosphere absorb specific wavelengths of light. By examining the resulting spectrum, scientists can identify the chemical composition of the atmosphere. For example, the James Webb Space Telescope, JWST, uses infrared spectroscopy to analyze the atmospheres of exoplanets, looking for key gases like oxygen, methane, and water vapor, which could signal biological activity. Direct imaging, although challenging due to the vast distances and the brightness of host stars, is another method gaining traction. Coronagraphs and starshades are technological innovations that help block the star's light, enabling telescopes to capture reflected light from the planet itself. The spectra obtained from this reflected light can provide detailed information about the planet's atmosphere, surface conditions, and potential biosignatures. Future missions like the proposed Large UV/Optical/IR Surveyor, LUVOIR, aim to employ these technologies to directly image Earth-like exoplanets and their potential signs of life. Transit observations offer yet another avenue. When a planet transits its star, it causes a slight dimming of the star's light. Analyzing these light curves helps determine the planet's size, orbit, and even hints of atmospheric conditions. Space telescopes like TESS, Transiting Exoplanet Survey Satellite, and its predecessor Kepler, have been instrumental in discovering thousands of exoplanets by this method. Moreover, by examining how the starlight changes during the transit, scientists can deduce the atmospheric composition. Ground-based telescopes also play a vital role in this hunt. Instruments like the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will possess the resolution and light-gathering capability to find and analyze exoplanetary atmospheres. These observatories, despite the challenges posed by Earth's atmosphere, offer higher resolution and the ability to conduct long-term observations. Combining these methodologies provides a multidimensional picture of exoplanets and their potential for harboring life. The ultimate goal is to find biosignatures, definitive evidence of life processes, in the form of particular atmospheric gases, surface features, or even temporal changes in the planet's environment. Each detection or non-detection refines our models and hones the strategies for future explorations, bringing us ever closer to answering the profound question of whether we are alone in the universe. The Drake equation is a probabilistic formula developed by Dr. Frank Drake in 1961, aimed at estimating the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. Although it doesn't provide a definitive answer, it serves as a framework to guide scientific inquiries into the search for intelligent life beyond Earth. The equation breaks down the daunting question into more manageable subcomponents, each representing a variable that can be studied, measured, or estimated through astronomical and biological research. The Drake equation is often written like this: n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. In this equation, n represents the number of civilizations with which humans might communicate. Let's break down the variables. First, r star is the average rate of star formation in our galaxy. This is relatively well understood through astronomical observations, typically estimated to be around 1 to 3 stars per year. Second, f sub p is the fraction of those stars that have planetary systems. Observations from missions like Kepler and TESS have shown that planetary systems are quite common, with estimates suggesting that a significant majority of stars have planets. Third, n sub e represents the average number of planets that could potentially support life per star that has planets. This includes Earth-like planets situated in the habitable zone where conditions might allow for liquid water. Current estimates vary widely, but ongoing research is continuously refining this number. Fourth, f sub l is the fraction of planets where life actually appears. This is one of the more speculative factors, as it is based on our limited understanding of how life originates. Earth is our only data point, making this estimate highly uncertain. Fifth, f sub I pertains to the fraction of life-bearing planets where intelligent life emerges. This also remains speculative because it requires a deep understanding of the evolutionary processes that lead to intelligence. Sixth, f sub c stands for the fraction of civilizations that develop technology capable of sending detectable signals into space. This includes technologies like radio telescopes and other forms of electromagnetic communication. Seventh, L is the length of time these civilizations release detectable signals into space. This could be influenced by a variety of factors, including the longevity of a civilization, technological advancements, or even self-destruction. By multiplying these terms, the Drake equation provides a framework to estimate n, sparking both scientific curiosity and philosophical debates. While the values of the variables are imprecise and highly debated, the equation itself has been instrumental in guiding research programs like SETI, Search for Extraterrestrial Intelligence. It encourages a multidisciplinary approach, integrating astronomy, biology, and even sociology to tackle one of humanity's most profound questions: are we alone in the universe? Europa, one of Jupiter's moons, is a prime candidate in the search for extraterrestrial life because it is believed to harbor a vast subsurface ocean beneath its icy crust. Scientists have devised several innovative missions and technologies to explore this hidden ocean, aiming to understand its composition, dynamics, and potential for supporting life. NASA's upcoming Europa Clipper mission, set to launch in the early 2020s, is a flagship endeavor in this quest. The spacecraft will conduct detailed reconnaissance of Europa's ice shell and underlying ocean, using a suite of sophisticated instruments. Among these are ice-penetrating radar to map the thickness of the ice and identify subsurface lakes, spectrometers to analyze the surface composition, and magnetometers to detect the salinity and depth of the ocean by studying variations in Europa's magnetic field. High-resolution cameras will capture detailed images of the surface, revealing features like ridges, cracks, and potential plumes of water vapor erupting through the ice from the ocean below. The possibility of water plumes shooting up from Europa's surface, first hinted at by the Hubble Space Telescope, presents an exciting opportunity for direct sampling. If confirmed during the Clipper mission, these plumes could be analyzed by flying the spacecraft through them, allowing for the collection of water vapor and ice particles without the need to drill through the ice. Such samples could contain organic molecules or even microbial life, offering a tantalizing glimpse into the moon's habitability. In the longer term, ambitious proposals for landers and even submersibles are on the drawing board. One such concept is the Europa lander mission, which would aim to touch down on the surface and carry instruments capable of drilling through the ice to reach the ocean below. The lander would be equipped with tools for analyzing the chemical makeup of the ice and any potential organic compounds. More futuristic ideas include cryobots, robotic probes that would melt their way through the ice using heat, and deploy underwater drones, known as hydrobots, to explore the ocean directly. These submersible robots could be outfitted with cameras, lights, and sensors to navigate the dark, high-pressure environment, searching for signs of life and studying the ocean's properties in unprecedented detail. Exploring Europa's ocean requires overcoming significant technical challenges, from dealing with extreme radiation levels emanating from Jupiter to ensuring that spacecraft and probes are sterilized to prevent contamination with Earth life. Despite these challenges, the scientific community is optimistic that these missions will yield groundbreaking insights into one of the most intriguing environments in our solar system. By combining orbital reconnaissance, plume sampling, and eventually subsurface exploration, researchers hope to unlock the secrets of Europa's ocean and potentially discover the first evidence of life beyond Earth. Meteorites have served as invaluable messengers from space, providing a wealth of information about the early solar system, the building blocks of life, and even the potential for life elsewhere. These rocky fragments, which often originate from asteroids and sometimes from other planets and moons, can survive their fiery passage through Earth's atmosphere and land on our planet, where they are meticulously studied by scientists. One of the most significant insights we've gained from meteorites concerns the presence of organic molecules, which are the chemical precursors to life. For instance, the Murchison meteorite, which fell in Australia in 1969, has been found to contain over 90 different amino acids. Notably, some of these amino acids are not commonly found on Earth, indicating that organic chemistry processes occur naturally in space. This discovery supports the hypothesis that the early building blocks of life may have been delivered to Earth via meteorite impacts, possibly kickstarting the development of life. Meteorites also provide clues about the primordial conditions of the solar system. The analysis of isotopic ratios within these rocks, ratios of elements like hydrogen and carbon, helps scientists understand the processes that shaped the early solar system's matter. For example, chondrites, a class of stony meteorites, contain tiny spherical inclusions called chondrules, which offer insights into the conditions and processes of the solar nebula from which our solar system formed. Particularly intriguing are the Martian meteorites, like ALH 84001, which was found in Antarctica in 1984. This meteorite is believed to have been ejected from the surface of Mars by an asteroid impact and traveled through space before landing on Earth. Inside ALH 84001, scientists discovered tiny carbonate globules that some researchers initially interpreted as fossilized evidence of Martian microbial life. Although this interpretation remains controversial, the meteorite nonetheless revealed the past presence of liquid water on Mars and sparked significant interest in Mars as a habitable environment. Isotopic analysis of meteorites also helps discern the history of water in our solar system. For example, some meteorites contain minerals that suggest they once had water locked inside them. By studying these hydrated minerals, scientists gain insights into the distribution and history of water in the early solar system. This has implications not only for understanding Earth's water sources, but also for assessing the habitability of other celestial bodies. Meteorites have greatly enriched our understanding of life's potential in space and the early history of the solar system. They have revealed the presence of organic molecules and provided evidence of the chemical processes that could lead to life. They also offer clues about the history of water in space and the possible past habitability of planets like Mars. Through these extraterrestrial rocks, we continue to piece together the puzzle of life's origins and distribution in the cosmos. Studying the potential for life on Mars is a comprehensive and multidisciplinary effort that involves a combination of robotic missions, remote sensing technology, and Earth-based laboratory research. Scientists focus on understanding Mars' past and present environment, searching for signs of water, organic molecules, and other conditions conducive to life. Robotic missions have been at the forefront of this investigation. NASA's Mars rovers, such as Spirit, Opportunity, Curiosity, and the recently landed Perseverance, are equipped with an array of sophisticated instruments designed to explore the Martian surface. Spirit and Opportunity revealed evidence of ancient water flows through the discovery of minerals and geological formations that form in the presence of water. Curiosity, which landed in Gale Crater in 2012, has analyzed rock samples and found organic molecules, complex carbon-based compounds that are essential to life. It also discovered evidence that Gale Crater once hosted a lake with conditions that could have been habitable for microbial life. Perseverance is taking this search to the next level. Equipped with advanced scientific tools, including the Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, and PXL, planetary instrument for X-ray lithochemistry instruments, Perseverance is searching for biosignatures and drilling core samples of Martian rocks. These samples are being cached for a future mission to return to Earth, where they can be analyzed in state-of-the-art laboratories, potentially providing definitive evidence of past life. Remote sensing technology also plays a crucial role. Orbiters such as NASA's Mars Reconnaissance Orbiter, MRO, and the European Space Agency's Mars Express use high-resolution cameras and spectrometers to analyze the planet's surface and atmosphere from above. These orbiters can identify mineral deposits, map ice distributions, and even detect subsurface water through radar. Observations from these spacecraft help scientists identify promising landing sites for future missions and provide a broader context for the findings of surface rovers. Mars' seasonal methane emissions offer another intriguing line of investigation. Methane can be produced by geological processes, but on Earth, a significant amount of methane is produced biologically. The periodic detection of methane in Mars's atmosphere, as observed by both instruments on the Curiosity rover and the Trace Gas Orbiter, raises the exciting possibility that microbial life could exist on Mars today, although non-biological explanations remain possible and are actively studied. Laboratory research on Earth complements these efforts. Scientists study Mars' analog environments, places on Earth that mimic Martian conditions, such as the Atacama Desert in Chile or the dry valleys of Antarctica. These studies help researchers understand how life can persist in extreme conditions and develop techniques for detecting life that can be applied on Mars. Researchers also perform experiments that simulate Martian environmental conditions to test the survival and adaptability of microorganisms. The search for life on Mars is a multifaceted endeavor that integrates robotic explorers, orbiters, laboratory simulations, and multidisciplinary scientific research. By compiling data from surface missions, orbital observations, and Earth-based studies, scientists are piecing together the history of Mars' climate and geology, searching for chemical evidence of life, and laying the groundwork for future human exploration that may finally answer whether life ever existed on the Red Planet. The discovery of phosphine on Venus has stirred significant excitement and debate within the scientific community, as it suggests the potential for life or unknown geochemical processes in its atmosphere. Phosphine, pH3, is a molecule composed of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is produced by industrial processes or by anaerobic, oxygen-free ecosystems, including microbial activity. Its detection on Venus is intriguing because it raises questions about the potential for biological or chemical processes occurring there that are not yet understood. The discovery was made using observations from the James Clerk Maxwell Telescope, JCMT, in Hawaii, and confirmed by the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. These instruments detected a spectral signature consistent with phosphine in the clouds of Venus, where temperatures are relatively moderate compared to the searing surface below. The concentrations detected were much higher than could be accounted for by known abiotic processes, such as volcanic activity, lightning, or reactions involving sunlight and minerals. The significance of this finding lies primarily in the context of astrobiology and planetary science. Phosphine is a potential biosignature gas because on Earth, its production is largely associated with life processes. If the phosphine on Venus is indeed biogenic, it could imply that microbial life exists in the temperate but highly acidic clouds of the planet, challenging our understanding of where life can thrive. However, it is crucial to exercise caution. The detection of phosphine does not necessarily mean life exists on Venus. There are many unknowns and complexities regarding Venusian chemistry. The discovery has prompted scientists to propose alternative, non-biological mechanisms that might explain the presence of phosphine. For instance, there could be exotic chemical reactions happening under the extreme conditions in the Venusian atmosphere that we do not yet understand. To build upon this discovery, further observations and missions are essential. Upcoming missions like NASA's Veritas, Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, and ESA's Envision aim to provide more detailed analyses of Venus's atmosphere and geological features. These missions could help discern whether the detected phosphine is a byproduct of unknown abiotic processes or a potential indicator of life. The discovery of phosphine on Venus is significant because it opens new avenues for research into both planetary science and the search for extraterrestrial life. It challenges our current understanding of atmospheric chemistry and underscores the need for further exploration of Venus's atmosphere to determine the true nature of this enigmatic molecule. The findings have reignited interest in Venus, often overshadowed by Mars, as a candidate in the quest to answer one of humanity's most profound questions: are we alone in the universe? When scientists classify exoplanets in terms of habitability, they often focus on a variety of factors that determine whether these distant worlds could potentially support life. First and foremost is the concept of the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where the temperature is just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it. For instance, a planet that's located too close to its star might experience extreme temperatures that would boil any surface water away, while one too far might be so cold that water would remain perpetually frozen. Beyond the habitable zone, scientists also look at factors like the planet's atmosphere, size, and composition. A thick atmosphere rich in greenhouse gases such as carbon dioxide can trap heat and maintain liquid water, even if the planet is on the colder edge of the habitable zone. Conversely, an atmosphere that's too thin might not be able to support stable surface conditions. The planet's size is also crucial. Those that are too small may not have sufficient gravitational pull to hold onto an atmosphere, while those that are too large could become gas giants with hostile environments. Additionally, the presence of elements such as oxygen and nitrogen in the atmosphere could indicate chemical processes that are potentially conducive to life. With advancements in technology, including space telescopes and spectrometers, scientists continue to refine these criteria, making the exciting search for habitable exoplanets more precise and hopeful. Mars, often dubbed the Red Planet, once possessed vast amounts of water, as evidenced by ancient river valleys, lake beds, and minerals that could only have formed in the presence of water. However, over billions of years, Mars lost much of its water, transforming it into the cold, arid desert we see today. One of the main reasons for this dramatic change lies in the planet's loss of its magnetic field. Unlike Earth, Mars lacks a global magnetic field, which left its atmosphere exposed to solar wind, streams of charged particles emitted by the sun. These particles gradually eroded Mars's atmosphere, thinning it to the point where it could no longer support substantial surface water. The restoration of water on Mars, while theoretically conceivable, presents formidable challenges. One proposed idea involves terraforming, a process that would modify Mars's environment to make it more Earth-like. For instance, some scientists speculate about the possibility of using greenhouse gases to artificially warm the planet. Introducing these gases could potentially thicken the atmosphere and increase surface temperatures, allowing for the stabilization of liquid water. Another idea is the concept of targeting icy asteroids or comets to crash into Mars, thereby delivering a fresh supply of water. While these ideas are innovative, they are also fraught with technical, ethical, and ecological complexities. Whether such techniques will ever be feasible remains a topic of tantalizing speculation and active research in the scientific community. Proxima b, an intriguing exoplanet orbiting Proxima Centauri, the closest star to our solar system, has captured significant attention since its discovery. Situated just over 4 light-years away, Proxima b is located within its star's habitable zone, meaning it has the potential to support liquid water, a crucial ingredient for life as we know it. Despite this promising position, Proxima b's potential habitability involves numerous complex factors that scientists are eager to explore. One significant challenge is Proxima Centauri itself. This star is a red dwarf, known for its volatile and violent cosmic behavior. Red dwarfs can emit powerful stellar flares that bombard nearby planets with high levels of radiation, potentially stripping away atmospheres and rendering the surface inhospitable. Proxima B's proximity to its star, completing an orbit in just 11 days, places it in the direct path of such flares. However, the exoplanet's ability to retain an atmosphere, potentially bolstered by a strong magnetic field, could mitigate some of these effects. Moreover, the composition and reflective properties of any atmosphere it might have could influence its surface conditions, either maintaining a stable climate or contributing to its volatility. While these questions currently remain unanswered, ongoing research and future missions aim to delve deeper into Proxima B's characteristics, inching us closer to understanding whether this distant world could indeed harbor life. Walking on Titan, Saturn's largest moon, would be an experience unlike any other in the solar system. Titan is the only moon with a dense atmosphere, primarily composed of nitrogen with a precious hint of methane. With a surface pressure about 1.5 times that of Earth, you would feel a gentle yet noticeable resistance as you moved. Titan's gravity is just 14% of Earth's, so each step would be a lightweight, almost bounding experience, allowing you to cover more ground with less effort. As you trod across Titan's surface, you'd encounter a landscape that straddles the familiar and the alien. Vast, flat plains of frozen water ice mixed with hydrocarbons would unfurl before you, occasionally interrupted by dunes made of dark organic material similar to soot. Lakes and seas of liquid methane and ethane dot the polar regions, giving an otherworldly twist to features reminiscent of Earth's own hydrological cycle. These liquid hydrocarbons, though frigid at -290 degrees Fahrenheit, flow and pool in a manner akin to water on Earth. The light from the distant sun, filtered through Titan's thick, hazy atmosphere, would take on a muted orange hue, casting an eerie yet enchanting glow over the surreal landscape. Equipped with appropriate thermal protection to guard against the extreme cold, your journey would evoke a sense of wonder and discovery on this remarkably Earth-like yet profoundly different world. Super-Earths, a class of exoplanets with masses ranging from about 1 to 10 times that of Earth, present a fascinating array of differences and unique characteristics compared to our home planet. Unlike Earth, super-Earths can vary significantly in their composition. Some may be rocky like Earth, while others could possess thick atmospheres filled with hydrogen or be rich in water. Their larger masses bestow them with stronger gravitational pulls, which can dramatically influence their geophysical and atmospheric dynamics. For instance, a stronger gravitational field might enable these planets to retain thicker atmospheres, potentially offering better protection from cosmic and solar radiation and fostering more stable climates. The diversity of super-Earths extends to their potential habitability and geological activity. On one end of the spectrum, some super-Earths may have active plate tectonics, driven by robust internal heat that can support dynamic geology similar to Earth's. Such tectonic activity can play a crucial role in recycling carbon and other elements essential to maintaining long-term climate stability. On the other hand, super-Earths with substantial water content, sometimes referred to as water worlds, might have global oceans covering their entire surfaces, leading to environments profoundly different from our terrestrial experience. The exact nature of these oceans, whether shallow or thousands of kilometers deep, remains an area of active scientific investigation. This rich variety makes super-Earths intriguing candidates in the search for extraterrestrial life, offering a glimpse into how planets similar yet distinct from our own might develop and sustain life in the universe. The idea of life in the cloud layers of Venus might seem improbable at first glance, given the planet's extreme surface conditions, temperatures hot enough to melt lead and crushing atmospheric pressures. However, the upper cloud layers of Venus present a surprisingly more temperate and intriguing environment where the possibility of life has garnered scientific interest. At altitudes of about 30 to 60 kilometers above the surface, temperatures range from a balmy 30 to 200 degrees Fahrenheit, with pressure levels resembling those found on Earth's surface. These more forgiving conditions have led some scientists to speculate that microbial life could theoretically exist in this region. The composition of Venus's clouds, however, poses both challenges and signs of potential habitability. The clouds are primarily composed of sulfuric acid, an inhospitable environment for life as we know it. Nevertheless, some extremophiles on Earth, microorganisms thriving in highly acidic environments, suggest that life might find a way to survive even in these harsh conditions. The recent detection of phosphine gas, a potential biosignature, caught the attention of the scientific community. Phosphine is known to be produced by biological processes on Earth, and its presence in Venus's atmosphere, detected in quantities far too substantial to explain by known abiotic chemistry alone, hints at the tantalizing possibility of microbial inhabitants. While this idea is far from confirmed, it has reignited interest in Venus exploration. Future missions are being planned to probe deeper into these mysterious clouds, employing advanced instruments to detect signs of life or understand the chemical processes at work. This vision of potential life in Venus's temperate cloud decks not only broadens our understanding of where life could thrive in the universe, but also challenges our assumptions about life's resilience under extreme and unexpected conditions. The phenomenon of diamond rains on Neptune and Uranus, two of the most enigmatic planets in our solar system, is a result of their unique internal conditions and composition. Both ice giants are rich in hydrocarbons like methane, which plays a crucial role in the formation of these exotic precipitations. Deep within the planets, pressures reach millions of times that of Earth's atmosphere, while temperatures soar to several thousand degrees Celsius. Under such extreme conditions, methane molecules decompose, releasing hydrogen and carbon atoms. The liberated carbon atoms then bond together, forming long chains that ultimately crystallize into diamonds. These diamonds rain down through the planet's layers, much like water droplets falling through Earth's atmosphere. As they descend, the pressure and temperature increase, driving them deeper into the interior. Eventually, these diamond crystals might form a hot, dense layer around the planet's core, adding a strikingly exotic twist to our understanding of planetary geology. This remarkable process was first surmised through laboratory experiments and sophisticated computer models that simulated the intense conditions within Neptune and Uranus. Scientists have successfully created similar conditions in the lab by using high-powered lasers to mimic the immense pressures and temperatures believed to exist inside these planets. These experiments have provided compelling evidence to support the theory of diamond rains. While this remains a largely theoretical concept, future missions to the outer planets may one day provide more direct observations, unlocking further mysteries about the inner machinations of our distant celestial neighbors. Beneath the icy crust of Enceladus, Saturn's intriguing moon, lies a subsurface ocean that has captured the fascination of scientists and enthusiasts alike. This small moon, only about 300 miles in diameter, reveals its secrets through dramatic geysers that erupt from its south pole, spewing water vapor, icy particles, and organic compounds far into space. These plumes were first observed by the Cassini spacecraft, revealing clues about the composition and the conditions underneath the ice. The subsurface ocean of Enceladus is kept in a liquid state due to tidal heating. As Enceladus orbits Saturn, gravitational interactions generate frictional heat within the moon's interior, preventing the ocean from freezing solid. Analyses of the materials ejected by the geysers have detected salts, simple organic molecules, and even tiny grains of silica, suggesting that hydrothermal vents could exist on the ocean floor. These vents could provide energy and a rich concoction of chemicals, akin to similar environments on Earth, where life thrives in the absence of sunlight. The presence of molecular hydrogen in the plumes is particularly exciting because it could serve as a potential energy source for microbial life. The discovery of these features on Enceladus has profound implications for the search for extraterrestrial life. If microbial life or even more complex organisms can exist around hydrothermal vents on Earth, the similar conditions on Enceladus could potentially foster life as well. Future missions, equipped with advanced instruments capable of analyzing the chemical composition of the plumes in even greater detail, aim to probe this icy moon further. Enceladus remains a prime target in the quest to explore the possibility that life could exist elsewhere in our solar system, hidden beneath layers of ice on a distant, enigmatic moon. Rogue planets, also known as interstellar or free-floating planets, are fascinating celestial bodies that drift through the galaxy untethered to any star. Unlike the planets in our solar system that orbit the Sun, these planets do not have a parent star to provide light and energy. Their origins can be traced back to a couple of astrophysical processes. One primary theory suggests that rogue planets form in protoplanetary disks around young stars, much like ordinary planets. However, dynamic instabilities within these disks can lead to gravitational interactions that eject these planets from their stellar systems, sending them careening through the galaxy. Another possibility is that rogue planets form in isolation, directly from the collapse of gas and dust clouds in interstellar space. This mechanism, though less efficient, can give birth to planets in a manner somewhat analogous to star formation, yet without the mass to ignite nuclear fusion and become stars themselves. Once cast adrift, rogue planets traverse the galaxy at considerable velocities, influenced only by the gravitational pull of stars and other massive objects they pass by. Despite their isolation, rogue planets might host unique and extreme environments. For instance, a massive rogue planet with a thick atmosphere could retain heat generated from its initial formation or from radioactive decay within its core. This internal heat could allow the planet to maintain subsurface oceans or layers of ice, creating potential niches for life. Detecting these elusive wanderers is challenging due to the lack of starlight to illuminate them. However, advancements in space telescopes and techniques like gravitational microlensing, where the rogue planet bends the light of a distant star, are helping astronomers uncover these lonely travelers. The discovery and study of rogue planets open a new chapter in our understanding of planetary formation and the diverse possibilities for celestial bodies in the cosmos. Hot Jupiters are a class of exoplanets that are similar in size and composition to Jupiter, but orbit extremely close to their parent stars, often completing an orbit in a matter of days. These gas giants defy traditional planetary formation theories because they reside so close to their stars, typically within 1/10 the distance that Mercury orbits the Sun. The proximity results in scorching temperatures that can exceed 1,000 degrees Celsius, intensifying their atmospheric dynamics and making them some of the most exotic celestial objects known. One of the most compelling questions about hot Jupiters is how they end up in such tight orbits. The prevailing theory suggests that these planets initially form far from their stars, in much cooler and more stable regions, similar to where Jupiter formed in our solar system. Over time, gravitational interactions with the protoplanetary disk or other planetary bodies may cause these planets to migrate inward. This process, known as planetary migration, can be driven by disk-planet interactions where the planet loses angular momentum and spirals toward the star. Additionally, gravitational perturbations from other massive planets in the system can result in dynamic instabilities that fling the hot Jupiter into a shorter orbit. Once they reach their close-in positions, tidal forces between the planet and the star can further circularize and stabilize their orbits. The study of hot Jupiters has provided valuable insights into the complexities of planetary system dynamics and formation. These planets often have dramatic climatic and atmospheric features, including high-speed winds, intense storms, and temperature inversions caused by the heat from their parent stars. As a result, they serve as natural laboratories for understanding atmospheric chemistry and physics under extreme conditions. Their discovery challenged early models of planetary formation and has led to a richer and more intricate picture of the diverse planetary systems that populate our galaxy. The discovery of the TRAPPIST-1 system, with its 7 Earth-sized planets, has profoundly impacted our understanding of planetary systems and the potential for life beyond our solar system. Located just 40 light-years away, TRAPPIST-1's planets orbit a cool dwarf star, and 3 of these worlds reside in the habitable zone, where conditions might allow for liquid water. The sheer number of Earth-like planets in a single system suggests that such configurations may be more common than previously thought, significantly boosting the odds of finding other Earth-like environments in the galaxy. Before the discovery of TRAPPIST-1, most known exoplanets were either much larger than Earth or situated in orbits unsuited for life as we know it. TRAPPIST-1's 7 planets, all within a tight orbital range around their diminutive star, showcase a system very different from our own. This discovery has spurred scientists to reconsider the diversity of planetary environments that might exist and the variety of conditions under which life could potentially arise. The planets' proximity to each other and their star presents unique opportunities for detailed study, with each transit of the planets in front of their star providing valuable data about their atmospheres, compositions, and potential habitability. Moreover, TRAPPIST-1 has heightened interest in the role of red dwarf stars as potential hosts for habitable planets. While these stars are cooler and less luminous than our Sun, they are abundant in the galaxy, making up about 70% of all stars. If planets orbiting red dwarfs can support life, it dramatically increases the number of possible habitable worlds. Future telescopes and missions, such as the James Webb Space Telescope and the European Space Agency's Ariel mission, are poised to explore the TRAPPIST-1 system in unprecedented detail, seeking signs of atmospheres and potential biosignatures. The discovery of TRAPPIST-1's 7 Earth-like planets not only expands our cosmic perspective, but also invigorates the tantalizing search for life beyond Earth, suggesting that the universe may be teeming with diverse and potentially habitable worlds. Space telescopes like the Hubble Space Telescope operate by observing the universe from outside Earth's atmosphere, providing an unobstructed view of celestial objects. Unlike ground-based telescopes, Hubble isn't hindered by atmospheric distortions such as turbulence and light pollution, which can blur and dim images. This advantage allows Hubble to capture incredibly sharp and detailed images across multiple wavelengths, from ultraviolet through visible light to near-infrared. Hubble orbits the Earth approximately every 97 minutes at an altitude of about 340 miles. It collects light using a large primary mirror that is 2.4 meters in diameter. The light is then directed to its suite of scientific instruments, including cameras, spectrographs, and sensors. These instruments analyze the light, enabling Hubble to accomplish a variety of tasks, such as imaging distant galaxies, measuring the light spectra of stars and planets, and monitoring cosmic events like supernovae. These instruments can be periodically replaced or upgraded, thanks to servicing missions by astronauts, which maintain Hubble's cutting-edge capabilities. The process begins with the telescope's wide aperture gathering light, reflecting it off the primary mirror to a smaller secondary mirror, and then funneling it into the various instruments. Each instrument is tuned to specific goals, such as the Advanced Camera for Surveys, ACS, for capturing large fields of view, and the Cosmic Origins Spectrograph, COS, for detailed spectroscopic analysis. Data collected by these instruments are beamed back to Earth, where scientists analyze them to glean insights into the universe's composition, structure, and evolution. Hubble's groundbreaking contributions have revolutionized our understanding of the cosmos. From mapping dark matter and dark energy distributions to discovering exoplanets and studying the formation of galaxies, Hubble has continually pushed the boundaries of astronomical knowledge. Its success has paved the way for future space telescopes like the James Webb Space Telescope, which will build on Hubble's legacy, probing even deeper into the universe with enhanced capabilities and newer technologies. The Voyager missions, comprising Voyager 1 and Voyager 2, have been nothing short of revolutionary in expanding our understanding of the outer planets: Jupiter, Saturn, Uranus, and Neptune. Launched in 1977, these twin spacecraft were designed for a grand tour of the outer solar system, taking advantage of a rare planetary alignment that allowed them to visit multiple planets with minimal fuel consumption. The wealth of data and stunning images returned by the Voyagers have provided insights into the complex and dynamic worlds that orbit the Sun's fringes. At Jupiter, the Voyagers unveiled the planet's turbulent atmosphere, characterized by violent storms and colorful cloud bands. They also discovered active volcanism on the moon Io, the first such evidence outside Earth. This volcanic activity drastically altered our views on geological processes in the solar system. The mission also provided detailed images of the Great Red Spot and extensive data on Jupiter's magnetosphere. The spacecraft's journey to Saturn solidified our knowledge of the planet's intricate ring system. Voyager 1's close flyby revealed gaps and divisions within the rings, while Voyager 2 provided a thorough analysis, uncovering moonlets and complex interactions among the ring particles. Additionally, the missions delivered unprecedented views of Titan, Saturn's largest moon, shrouded in a thick atmosphere of nitrogen and methane. Voyager 2's continued mission to Uranus and Neptune marked humanity's first, and so far only, close encounters with these distant giants. At Uranus, Voyager 2 discovered a tilted magnetic field, dark rings and dynamic moons like Miranda, which displayed an unusually chaotic surface. At Neptune, the spacecraft observed supersonic winds and violent storms, including the Great Dark Spot, a massive storm system akin to Jupiter's Great Red Spot. It also provided close-ups of Triton, Neptune's largest moon, revealing geysers of nitrogen and a landscape sculpted by cryovolcanism. The Voyager missions have extended beyond these planetary visits and continue to send data from interstellar space. They have enriched our comprehension of the solar system's outer realms and remain a testament to human ingenuity and curiosity, continually expanding our horizons and spurring future explorations. Rovers exploring the surface of Mars are essentially mobile robotic laboratories designed to navigate the Martian terrain, conduct scientific experiments, and relay data back to Earth. Their exploration capabilities are powered by a combination of sophisticated engineering and advanced scientific instruments. These rovers are equipped with wheels or tracks designed to traverse the diverse and challenging Martian landscape, from rocky plains and sandy dunes to steep cliffs and ancient riverbeds. One of the primary features of Mars rovers is their autonomy. While mission control teams on Earth send high-level commands, the rovers are capable of making real-time decisions to navigate obstacles and choose paths. This is crucial given the time delay in communication between Earth and Mars, which can range from about 4 to 24 minutes one way. Rovers like Curiosity and Perseverance are fitted with onboard computing systems that process images from their cameras to detect hazards and map out safe routes. This autonomy allows them to cover more ground and conduct more science in a given time frame. The scientific instruments aboard Mars rovers are diverse and highly specialized. They typically include panoramic cameras to capture broad views of the landscape, microscopic imagers to study rock and soil textures, spectrometers to analyze the composition of materials, and environmental sensors to monitor weather conditions. For instance, Perseverance is equipped with the Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, instrument to detect organic compounds and minerals. It also carries the MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, to test the production of oxygen from Martian CO2, which is crucial for future human missions. Rovers often have robotic arms fitted with drills and scoops to collect and analyze soil and rock samples. For example, Curiosity's drilling system pulverizes rock samples, which are then analyzed by onboard laboratories like SAM, Sample Analysis at Mars, to detect organic molecules and gases. Perseverance goes a step further by caching rock and soil samples for potential return to Earth through future missions. These rovers communicate with Earth via relay satellites in Mars orbit, ensuring continuous data flow from the surface to mission control. The insights gained from these explorations have vastly enriched our understanding of Mars' geology, climate, and potential for ancient life, paving the way for future human exploration. The ongoing success of these robotic explorers underscores the incredible synergy of engineering and science in unveiling the secrets of the Red Planet. The International Space Station, ISS, serves as a multinational collaborative platform for scientific research, technological development, and international cooperation in space. Orbiting approximately 250 miles above Earth, the ISS is a unique microgravity and space environment laboratory where scientists and engineers conduct experiments across a multitude of disciplines, including biology, human physiology, physics, astronomy, and materials science. The insights gained from these experiments extend beyond the scope of space exploration, offering tangible benefits and advancements for life on Earth. One of the primary purposes of the ISS is to study the effects of long-term spaceflight on the human body. Astronauts living and working on the ISS spend months at a time in microgravity, providing crucial data on muscle atrophy, bone density loss, and changes in cardiovascular, neurovestibular, and immune systems. This information is vital for planning future deep space missions, such as trips to Mars, ensuring astronauts can withstand extended periods in space and return safely. In addition to human health research, the ISS is a hub for cutting-edge scientific experiments that exploit the unique conditions of space. For instance, microgravity enables the study of fluid dynamics, combustion, and material sciences in ways not possible on Earth. Protein crystal growth experiments on the ISS have offered new insights into medical treatments and drug development. The station's external platforms host a variety of instruments for Earth observation and space science, including monitoring cosmic rays, solar activity, and Earth's climate. The ISS also plays a significant role in fostering international collaboration in space exploration. It is a joint project involving 5 space agencies: NASA, United States; Roscosmos, Russia; JAXA, Japan; ESA, European Space Agency; and CSA, Canadian Space Agency. This international partnership sets a precedent for cooperation, sharing resources, expertise, and research across borders, which is essential for addressing global challenges and advancing humanity's presence in space. Educational outreach and inspiring the next generation of scientists, engineers, and explorers is another critical aspect of the ISS mission. Thousands of students worldwide engage with the ISS through live transmissions, educational programs, and scientific experiments conducted in their classrooms that are replicated on the station. By linking the wonders of space exploration with educational initiatives, the ISS helps cultivate curiosity and innovation in young minds, ensuring a continual investment in future space endeavors. Through its myriad of scientific, technological, and international functions, the ISS remains a cornerstone of human spaceflight, driving forward our understanding of living and working in space, and laying the groundwork for future exploration beyond low Earth orbit. Astronauts undergo extensive training that covers a broad spectrum of physical, technical, and psychological challenges to prepare for space missions. They spend countless hours in neutral buoyancy labs, massive swimming pools designed to simulate the microgravity conditions of space. By wearing spacesuits and working underwater, they practice tasks like repairing spacecraft or conducting experiments as they would while orbiting Earth. This underwater environment closely mimics the sensation of weightlessness, which helps astronauts get accustomed to the unique physical demands they'll face while floating through the International Space Station, ISS, or during spacewalks. In addition to physical training, astronauts receive intensive education in various scientific disciplines. They learn about the mechanical systems of spacecraft, how to handle potential emergencies, and even basic medical procedures. For example, they must know how to perform dental procedures or minor surgeries, as medical emergencies can't always be immediately addressed in space. They also spend time in flight simulators, replicating the conditions of spacecraft launches, landings, and operations in space. This holistic approach ensures that astronauts are mentally and physically prepared for the challenges of living and working in such an unforgiving environment. This rigorous preparation is crucial, as even the smallest error in space can have significant consequences. Long-duration space travel presents a plethora of challenges that are both physiological and psychological. One of the most significant physiological issues is the impact of microgravity on the human body. After spending weeks or months in space, astronauts often experience muscle atrophy and bone density loss. Studies show that astronauts can lose 1 to 2% of their bone mass per month in microgravity. To combat this, spacefarers engage in regular intensive exercise using specially designed resistance and cardiovascular equipment to maintain muscle mass and bone health. They also follow a carefully regulated diet rich in calcium and vitamin D to support bone density. Space travel also imposes considerable psychological challenges. The isolation, confinement, and distance from Earth can contribute to feelings of loneliness, depression, and anxiety. NASA and other space agencies are acutely aware of these issues and provide astronauts with psychological support. This includes regular communication with family and friends and access to mental health professionals. Crew members also engage in team-building exercises before the mission to foster strong interpersonal relationships and ensure effective communication. The constant presence of a small, enclosed group of people in a high-stress environment requires impeccable emotional intelligence and conflict resolution skills to maintain a healthy, cooperative living and working space. Given these challenges, long-duration space travel demands not only physical resilience, but also mental fortitude and adaptability. Planning missions to distant planets is an intricate and multifaceted process that involves several stages of rigorous analysis, design, and testing. The first step typically involves defining the scientific objectives of the mission, such as searching for signs of life, studying planetary geology, or understanding atmospheric conditions. Once the objectives are clear, scientists and engineers work together to design a spacecraft capable of achieving these goals. This includes selecting instruments and technologies that can withstand the harsh conditions of space and the target planet, which might involve extreme temperatures, intense radiation, or corrosive atmospheres. A crucial element of planning is trajectory design, which involves calculating the most efficient path to the destination. This process can take years of precise calculations and simulations, considering factors like the gravitational assists from other celestial bodies, fuel efficiency, and time constraints. For example, missions to Mars often use a Hohmann transfer orbit to minimize fuel consumption, a route that exploits the relative positions and motions of Earth and Mars for an optimal journey. Scientists also need to plan for contingencies, developing fail-safes and redundancy systems to address potential malfunctions or unexpected challenges. These meticulous preparations are complemented by rigorous testing phases, where spacecraft components are subjected to conditions mimicking space environments, ensuring everything works as expected before launch. The ultimate goal is to send a resilient, capable spacecraft that can navigate the cosmos while sending valuable data back to Earth. The Apollo moon landings provided a treasure trove of knowledge that has significantly advanced our understanding of both the moon and the broader cosmos. One of the most profound discoveries was the detailed geological data that astronauts collected, including lunar rocks and soil samples. These materials have been meticulously analyzed, revealing that the moon is roughly 4.5 billion years old, which is nearly as old as Earth itself. This finding helped scientists refine theories about the solar system's formation and the early processes that shaped the planets. Additionally, the composition of the moon rocks showed similarities to Earth's mantle, lending significant support to the prevailing theory that the moon originated from debris resulting from a colossal collision between Earth and a Mars-sized body. Beyond the geological insights, the Apollo missions demonstrated critical advancements in human spaceflight technology and logistics. The development of the Saturn V rocket, the only vehicle to have human-rated stages capable of reaching lunar orbit, showcased human ingenuity in engineering and rocketry. The missions also led to innovations in computer technology, materials science, and telecommunications that have since permeated various sectors on Earth. The lunar landings offered invaluable lessons in the complexities of space travel, from handling life support systems to navigating space vehicles with precision. The Apollo missions not only enriched our scientific understanding, but also laid the groundwork for current and future endeavors in space exploration, such as the Artemis program, which aims to return humans to the moon and eventually send astronauts to Mars. Protecting spacecraft from space debris is a critical concern for any mission, given that even small fragments can cause severe damage at high velocities. To address this, engineers employ a variety of strategies and technologies to safeguard spacecraft. One widely used method is the implementation of Whipple shields, named after astrophysicist Fred Whipple. These shields consist of multiple layers. The outermost layer is designed to absorb the energy of an impacting object, causing it to fragment into smaller pieces. The inner layers then absorb the remaining energy, effectively dissipating it before it can reach the critical components of the spacecraft. This multi-layered approach helps protect vital systems from being compromised. Another important aspect of space debris mitigation involves trajectory management and real-time monitoring. Space agencies like NASA and ESA, European Space Agency, continuously track thousands of pieces of space debris using ground-based radars and telescopes. This data is used to create predictive models that help identify potential collision threats. When a dangerous piece of debris is detected, the spacecraft can perform collision avoidance maneuvers, adjusting its orbit to move out of the way. These maneuvers require precise calculations and are typically automated to respond swiftly to imminent threats. Additionally, international guidelines and best practices are in place to minimize the creation of new debris, such as designing spacecraft with end-of-life disposal plans like deorbiting satellites or moving them to a graveyard orbit. Collectively, these protective measures are crucial for ensuring the longevity and safety of operational spacecraft amidst the growing challenge of space debris. The future of human space exploration is poised to be one of the most exciting chapters in the history of science and technology. One of the foremost objectives is the return of humans to the Moon through NASA's Artemis program. Set to start in the mid-2020s, Artemis aims not only to land the first woman and next man on the lunar surface, but also to establish a sustainable human presence by the end of the decade. This will involve the construction of the Lunar Gateway, a space station orbiting the Moon that will serve as a staging point for missions to the lunar surface and beyond. The experience gained from living and working on the Moon will be invaluable in preparing for even more ambitious missions, such as sending humans to Mars. Mars, often referred to as the next giant leap, represents the ultimate goal for many space exploration advocates. NASA and private companies like SpaceX are working diligently on the technologies required for such a monumental endeavor. These technologies include advanced propulsion systems, life support, and habitats that can shield astronauts from the harsh Martian environment. The journey to Mars will involve challenges like prolonged exposure to cosmic radiation, psychological stresses of extended isolation, and the need for sustainable life support and food production systems. However, the potential rewards, such as the search for past or present life and the opportunity to develop a multi-planetary human presence, make these challenges worth tackling. Additionally, international collaborations are expected to play a crucial role in the future of space exploration. Countries around the globe are joining forces to pool resources and expertise, as seen in projects like the International Space Station. These collaborations will likely extend to lunar bases and Martian exploration, fostering a new era of global cooperation. With advances in technology and international partnerships, humanity stands on the brink of exploring and potentially colonizing other worlds, opening up unimaginable possibilities for scientific discovery and the enduring legacy of human endeavor. As we journey through the cosmos, exploring the wonders and mysteries of space, it's important to understand the foundations upon which our current knowledge and future aspirations are built. The history of space exploration is not just a record of past achievements, but a roadmap that guides us towards future discoveries. By looking back at the milestones that brought us to this point, we can better appreciate the challenges and triumphs that shape our ongoing quest to reach further into the universe. The history and future of space exploration are filled with remarkable achievements and ambitious plans that continue to push the boundaries of what we know and where we can go. This journey began with an intense rivalry that propelled humanity into the cosmos, leading to significant milestones and setting the stage for an even more promising future. The space race between the United States and the Soviet Union profoundly shaped the early years of space exploration. This era of intense competition was fueled by the geopolitical tensions of the Cold War, driving both nations to achieve unprecedented feats. In 1957, the Soviet Union launched Sputnik, the first artificial satellite, into orbit, marking the beginning of the space age. This achievement shocked the world and spurred the United States to accelerate its own space efforts. The Soviets continued their lead by sending the first human, Yuri Gagarin, into space in 1961. Gagarin's historic flight demonstrated that human space travel was possible and ignited a fervent response from the United States. In response, the United States launched Project Mercury, which aimed to send the first American astronauts into space. Following Mercury, Project Gemini further advanced spaceflight capabilities by developing techniques for long-duration missions, spacewalks, and orbital rendezvous. These projects laid the groundwork for the Apollo program, which aimed to land humans on the Moon. The Apollo missions are among the most significant achievements in the history of space exploration. Apollo 11's successful moon landing in 1969 fulfilled President John F. Kennedy's bold vision and demonstrated the potential for human space exploration. The subsequent Apollo missions provided invaluable scientific data, including samples of lunar rock and soil, which have offered insights into the Moon's composition and geological history. Following the Apollo era, the Space Shuttle program revolutionized human spaceflight. Unlike the expendable rockets used previously, the Space Shuttle was designed to be reusable, significantly reducing the cost of sending humans and cargo into space. The program's fleet of orbiters conducted numerous missions, including deploying satellites, conducting scientific experiments, and assembling the International Space Station, ISS. The Space Shuttle program also played a crucial role in fostering international collaboration, as astronauts from many countries participated in missions. The lessons learned from the Space Shuttle program have informed the design of new spacecraft and missions. The Hubble Space Telescope, launched in 1990, has transformed our understanding of the universe. Orbiting above Earth's atmosphere, Hubble has provided stunning images and data, allowing scientists to study distant galaxies, nebulae, and other celestial phenomena with unparalleled clarity. Hubble's observations have led to groundbreaking discoveries, such as the accelerating expansion of the universe, the presence of supermassive black holes at the centers of galaxies, and detailed views of the formation and evolution of stars. Hubble's legacy continues as it works alongside newer observatories like the James Webb Space Telescope. Robotic exploration of Mars has achieved significant milestones over the decades. The Viking missions in the 1970s were the first to land safely on Mars and conduct experiments on its surface, searching for signs of life and analyzing the Martian soil. These early missions laid the groundwork for subsequent explorations. More recently, rovers such as Spirit, Opportunity, Curiosity, and Perseverance have explored Mars's terrain, studying its geology, climate, and potential for past life. These rovers have provided a wealth of data, revealing evidence of ancient rivers and lakes, and helping scientists understand the planet's habitability. Perseverance, in particular, is tasked with searching for signs of ancient microbial life and collecting samples for future return to Earth. International cooperation has been crucial in constructing and operating the International Space Station, ISS. The ISS is a symbol of what humanity can achieve when working together. Contributions from countries around the world have led to the creation of a unique laboratory in low Earth orbit. The ISS serves as a platform for scientific research, technological development, and international collaboration. Research conducted on the ISS spans a wide range of fields, from biology and physics to astronomy and materials science. The experience gained from living and working in space on the ISS is invaluable for future long-duration missions to the Moon, Mars, and beyond. The Artemis program is NASA's current initiative to return humans to the Moon and establish a sustainable presence there by the end of this decade. This ambitious program aims to land the first woman and the next man on the lunar surface. The goals of Artemis include advancing lunar science, demonstrating new technologies, and preparing for future human missions to Mars. However, the program faces numerous challenges, including developing new spacecraft, ensuring astronaut safety, and building the necessary infrastructure on the lunar surface. Artemis represents a critical step in expanding human exploration beyond low Earth orbit and establishing a foothold on another celestial body. Private companies like SpaceX and Blue Origin are revolutionizing space travel and exploration. SpaceX, founded by Elon Musk, has developed the Falcon and Starship rockets, which are designed for reusability, significantly reducing the cost of access to space. SpaceX's achievements include delivering cargo to the ISS, launching astronauts into space, and planning missions to the Moon and Mars. Blue Origin, founded by Jeff Bezos, is focused on building a road to space through reusable rockets and lunar landers. These companies are driving innovation, increasing competition, and opening new possibilities for space exploration, such as space tourism and commercial missions. Future missions are planned to explore the moons of Jupiter and Saturn, which are considered some of the most promising places to search for signs of life beyond Earth. NASA's Europa Clipper mission aims to investigate Europa, an icy moon of Jupiter with a subsurface ocean that may harbor conditions suitable for life. The mission will study the moon's ice shell, subsurface ocean, and potential plumes of water vapor. Similarly, missions to Saturn's moon Titan, such as the Dragonfly drone, will explore its thick atmosphere and surface, searching for clues about prebiotic chemistry and the potential for life. Titan's lakes and seas of liquid methane and ethane present a unique environment for scientific study. Advancements in propulsion technology, such as ion drives and nuclear propulsion, could enable interstellar travel. Ion drives, which use electrically charged ions to create thrust, provide a highly efficient means of propulsion suitable for long-duration missions within our solar system. These drives have been used successfully in missions like NASA's Dawn spacecraft, which explored the asteroid belt. Nuclear propulsion could offer even greater speeds, potentially enabling human exploration of the outer planets and beyond. By harnessing the power of nuclear reactions, spacecraft could achieve much higher velocities, reducing travel time to distant destinations. These technologies represent the next frontier in our quest to explore the cosmos, opening the door to missions that were once considered science fiction. Space exploration continues to evolve, driven by international collaboration, technological innovation, and the enduring human spirit of discovery. The achievements of the past and the ambitious plans for the future inspire us to keep reaching for the stars, uncovering the mysteries of the universe, and expanding the horizons of human potential. The journey into space is far from over, and each step brings us closer to understanding our place in the cosmos. As we look to the future, we can anticipate even more extraordinary discoveries and achievements that will continue to shape our understanding of the universe and our role within it. Auroras, often referred to as the northern and southern lights, are captivating natural light displays typically seen near the Earth's polar regions. These enchanting lights are caused by interactions between the solar wind and Earth's magnetosphere. The solar wind is a stream of charged particles, primarily protons and electrons, emitted by the sun. When these particles reach Earth, they encounter our planet's magnetic field, which funnels them toward the polar regions. Upon reaching the upper atmosphere, these charged particles collide with gas molecules such as oxygen and nitrogen. These collisions transfer energy to the gas molecules, exciting them and causing them to release light as they return to their normal state. The specific colors of an aurora depend on the type of gas and its altitude. For instance, oxygen typically emits green and red light, while nitrogen can produce blue and purple hues. The resulting light displays can range from faint glows to dramatic shimmering curtains of color that dance across the night sky. The best places to witness an aurora are near the polar regions, within the so-called auroral zones. The northern lights, or aurora borealis, are most commonly observed in high-latitude regions like Scandinavia, Canada, Alaska, and Russia. The southern lights, or aurora australis, can be seen from southern parts of Australia, New Zealand, and Antarctica. The frequency and intensity of auroras are influenced by solar activity, with peaks during periods of high solar activity, such as solar maximums within the 11-year solar cycle. For those keen to witness this spectacular phenomenon, timing a visit during these peak periods on clear, dark nights significantly enhances the chance of seeing one of nature's most breathtaking spectacles. Meteor showers are one of the most awe-inspiring celestial events, captivating stargazers with streaks of light darting across the night sky. They occur when Earth passes through the trail of debris left by a comet. As comets travel through space, they leave behind a stream of particles, dust, and small rocks, known as meteoroids, along their orbital path. When Earth's orbit intersects with these debris trails, the meteoroids enter our atmosphere. Upon entering the atmosphere, meteoroids encounter rapid deceleration due to friction with air molecules, creating intense heat and causing them to vaporize in a flash of light. This luminous phenomenon is what we see as a meteor or shooting star. Most of these meteoroids are quite small, often no larger than a grain of sand, but they travel at incredible speeds, ranging from 11 to 70 kilometers per second. Despite their size, their high velocity results in the bright, fleeting streaks of light observed during a meteor shower. The timing and frequency of meteor showers are predictable as they are associated with specific comets whose orbits Earth regularly crosses. For example, the Perseid meteor shower, one of the most famous, occurs annually in August when Earth intersects the debris trail of Comet Swift-Tuttle. Similarly, the Leonid meteor shower peaks in November, originating from the debris of Comet Tempel-Tuttle. Optimal viewing conditions for meteor showers include clear, dark skies away from city lights during the shower's peak times, typically in the hours after midnight. By observing during these peak periods, enthusiasts can often see dozens to hundreds of meteors per hour, creating a magnificent spectacle. Solar flares and coronal mass ejections, CMEs, are two of the most powerful phenomena originating from the Sun, carrying immense energy and having significant implications for both our planet and space exploration. A solar flare is a sudden, intense burst of radiation emanating from the Sun's atmosphere, typically occurring in regions with strong magnetic fields near sunspots. These flares release a vast amount of energy equivalent to millions of hydrogen bombs exploding simultaneously. The electromagnetic radiation from solar flares, which includes X-rays and ultraviolet light, can reach Earth within minutes, potentially disrupting communication systems, GPS signals, and even power grids by inducing geomagnetic storms. Coronal mass ejections are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These ejections can carry billions of tons of coronal material and possess much more energy than solar flares, although the two events can be related. When a CME reaches Earth, which can take from 1 to several days, it interacts with Earth's magnetosphere. This interaction can compress the magnetosphere, induce magnetic storms, and result in heightened auroral activity, essentially causing spectacular northern and southern lights. While auroras are benign visual treats, CMEs can pose a risk to satellite operations, navigation systems, and even the crew aboard space stations by exposing them to elevated levels of radiation. The implications of solar flares and CMEs extend beyond technological disruptions. Understanding these solar phenomena is crucial for space weather forecasting, which helps mitigate the risks to astronauts and equipment in space, as well as to terrestrial technologies. By studying solar flares and CMEs, scientists can develop better predictive models, thereby enhancing our preparedness for such events and ensuring the resilience of critical infrastructure on Earth. Scientists study cosmic rays through a combination of ground-based and spaceborne instruments designed to detect and analyze these high-energy particles. Cosmic rays originate from various sources, including the Sun, supernova, and distant galaxies, and consist primarily of protons, atomic nuclei, and other subatomic particles. These particles travel through space at nearly the speed of light, carrying valuable information about the most energetic processes in the universe. One of the primary methods for studying cosmic rays involves ground-based detectors, such as those found in extensive air shower arrays. These detectors are spread across large areas to capture the cascade of secondary particles produced when cosmic rays collide with atoms in Earth's atmosphere. The Pierre Auger Observatory in Argentina and the Telescope Array project in Utah are prominent examples of such facilities. These observatories use a combination of scintillators, water Cherenkov detectors, and fluorescence telescopes to measure the energy, direction, and composition of cosmic rays as they strike the atmosphere and generate air showers. In addition to ground-based observatories, space-based instruments play a crucial role in cosmic ray research. Satellites like NASA's Advanced Composition Explorer, ACE, and the European Space Agency's Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station are designed to detect cosmic rays directly in space, where they are less affected by Earth's atmosphere. These instruments measure a wide range of cosmic ray energies and compositions, helping scientists understand their origins and propagation through the galaxy. By combining data from both ground-based and space-based detectors, researchers can develop comprehensive models of cosmic ray behavior, shedding light on fundamental astrophysical processes and contributing to our understanding of the universe. Quasars, or quasi-stellar objects, are among the most luminous and enigmatic entities in the universe. They are the extremely bright centers of distant galaxies, thought to be powered by supermassive black holes that consume surrounding gas and dust. As matter spirals into the black hole's accretion disk, it heats up to incredibly high temperatures, emitting enormous amounts of electromagnetic radiation across the entire spectrum, from radio waves to visible light to X-rays. This intense luminosity allows quasars to outshine entire galaxies despite their compact size. The significance of quasars extends far beyond their stunning brightness. They serve as crucial probes for understanding the early universe. Most quasars are located billions of light-years away, meaning we see them as they were in the distant past. Observing quasars provides astronomers with snapshots of the early stages of galactic evolution. They reveal information about the conditions that prevailed when the universe was young, helping us comprehend how galaxies and their central black holes have evolved over cosmic time. Quasars also play an essential role as cosmic beacons that illuminate the intergalactic medium. As their light travels through the universe, it interacts with and is absorbed by intervening gas clouds. By studying the absorption lines in quasar spectra, scientists can analyze the composition, temperature, and distribution of matter in the vast spaces between galaxies. This helps in mapping the large-scale structure of the universe and understanding the processes that govern cosmic evolution. Furthermore, the study of quasars has led to critical advancements in cosmology, including more accurate measurements of the universe's expansion rate and insights into the distribution of dark matter. Through these luminous beacons, quasars illuminate not just the far reaches of the universe, but also the dynamic processes shaping its development. Magnetars are a fascinating and unique subclass of neutron stars that stand out due to their incredibly intense magnetic fields. While all neutron stars are the remnants of massive stellar explosions, known as supernovae, magnetars possess magnetic fields that are trillions of times stronger than Earth's magnetic field and up to 1,000 times stronger than those of typical neutron stars. These fields are so powerful that they can affect atomic structures and influence the behavior of matter in unprecedented ways. The intensity of a magnetar's magnetic field gives rise to some extraordinary phenomena. One of the most striking is the emission of high-energy electromagnetic radiation, particularly in the form of X-rays and gamma rays. Magnetars can experience dramatic episodes known as starquakes, where their crusts fracture due to the stress induced by the intense magnetic fields. These starquakes release vast amounts of energy, resulting in powerful bursts of radiation detectable across the cosmos. The decay of their magnetic fields over time also generates persistent, highly energetic emissions, distinguishing magnetars from other neutron stars that typically emit via more stable processes such as spinning and cooling. The extreme properties of magnetars offer valuable insights into the physics of neutron stars and the behavior of matter under the most extreme conditions. By studying magnetars, scientists hope to better understand the complexities of stellar evolution, the state of matter at nuclear densities, and the dynamics of extraordinarily strong magnetic fields. Moreover, the unique emissions from magnetars provide essential clues about the processes occurring in and around these exotic objects, helping to advance our broader understanding of astrophysical phenomena and the universe's fundamental forces. The Oort cloud is a theoretical, vast spherical shell of icy objects that is believed to surround the outer edges of our solar system, extending from roughly 2,000 to 100,000 astronomical units (AU) from the Sun. This cloud is thought to be the source of most long-period comets, which have orbits that take them well beyond the planets and into the far reaches of the solar system. Named after the Dutch astronomer Jan Oort, who first proposed its existence in the mid-20th century, the Oort cloud remains a largely hypothetical construct because it lies far beyond the reach of our current observational capabilities. The significance of the Oort cloud lies in its role in understanding the early solar system and the dynamics of cometary bodies. It is believed to be a remnant of the primordial disk of material that formed the Sun and planets. By studying comets that originate from the Oort cloud, scientists can gain insights into the conditions and processes that prevailed during the solar system's formation over 4 billion years ago. These comets are essentially time capsules, preserving the pristine material from which the solar system was born. Moreover, the Oort cloud plays a critical role in the gravitational interactions within our solar system and between our solar system and the galaxy. The influence of passing stars, as well as tidal forces from the Milky Way's gravitational field, can perturb the orbits of Oort cloud objects, sending them on trajectories that bring them into the inner solar system as comets. Understanding these dynamics helps scientists predict when and how long-period comets might appear and study their interactions with the planets. While the Oort cloud itself is yet to be directly observed, Its existence is inferred from the behavior of these comets, making it a significant focus of theoretical and observational astronomy. Tidal forces, generated by gravitational interactions between celestial bodies, have profound effects on the shape, behavior, and internal dynamics of these objects. These forces arise because the gravitational pull of one body varies with distance, creating a differential gravitational effect across another body. For instance, the side of Earth facing the Moon experiences a stronger gravitational pull than the side facing away, leading to tidal bulges in Earth's oceans. This same principle applies to other celestial bodies, influencing them in various impactful ways. On planetary scales, tidal forces are perhaps most famously observed in the Earth-Moon system, where they cause ocean tides. However, their influence extends far beyond this. Tidal interactions can lead to tidal locking, a process where a smaller body, such as a moon or a planet, rotates at the same rate it orbits, always showing the same face to its parent object. This is why we only see one side of the Moon from Earth. Tidal forces also cause internal friction within celestial bodies, generating significant heat, a phenomenon known as tidal heating. This heating is responsible for the volcanic activity on Jupiter's moon Io and the subsurface oceans on moons like Europa and Enceladus. In more extreme cases, tidal forces can tear celestial bodies apart, a process called tidal disruption. This occurs when the gravitational pull from a larger body, such as a planet or star, overcomes the structural integrity of a smaller object, such as a comet or an asteroid. Tidal disruption events are dramatic and can result in the smaller body being stretched into elongated shapes or even fragmented completely. For example, comets that pass too close to the Sun can be torn apart by the Sun's intense tidal forces. Understanding tidal forces is thus crucial in fields ranging from planetary science to astrophysics, as they play a key role in shaping the physical and dynamical evolution of celestial systems. Planetary nebulae are stunningly beautiful astronomical objects formed during the late stages of a star's life cycle, specifically for stars with masses up to about 8 times that of our Sun. Despite their name, planetary nebulae have no direct association with planets. The term was coined by early astronomers who observed these objects through small telescopes and thought they resembled the round, disc-like shapes of planets. The formation of a planetary nebula begins when a star exhausts the hydrogen fuel in its core, causing it to evolve into a red giant. During this phase, the star undergoes significant internal changes, including the fusion of helium into heavier elements in its core, while its outer layers expand and cool. Eventually, the outer layers are ejected into space due to strong stellar winds, leaving behind an exposed core. This core, now a hot white dwarf, emits intense ultraviolet radiation that ionizes the expelled gas, causing it to glow. This glowing gas forms the planetary nebula, which often appears as intricate, symmetrical structures with complex shapes and vibrant colors. These shapes can include rings, spheres, and even more elaborate forms, influenced by factors like magnetic fields, binary star companions, and the star's rotational velocity. The nebula typically persists for tens of thousands of years before dispersing into the interstellar medium, enriching it with heavier elements. These elements contribute to the formation of new stars and planets, making planetary nebulae vital to the ongoing cycle of matter in the galaxy. By studying planetary nebulae, astronomers gain insights into stellar evolution, nucleosynthesis, the creation of new elements within stars, and the chemical enrichment of the interstellar medium. The detailed structures and emissions of planetary nebulae also serve as natural laboratories for understanding the physics of ionized gases and the impact of stellar winds and radiation on surrounding material. Planetary nebulae are not only visually spectacular, but also fundamentally important to our comprehension of the life cycles of stars and the dynamic processes that shape our galaxy. Understanding the composition of distant planets and stars is an equilibrium act of science and technology, anchored in methods that turn light into a universal lexicon. One of the primary tools astronomers use is spectroscopy. When light from a star or planet passes through a prism, it splits into a spectrum of colors. Each element in the celestial body absorbs and emits light at specific wavelengths, creating a barcode-like pattern of lines within this spectrum, known as spectral lines. By comparing these lines to known patterns of elements observed on Earth, scientists can infer the chemical makeup of stars and planets, even those millions of light-years away. For instance, the hydrogen lines in a star's spectrum can reveal not just the presence of hydrogen, but also its abundance, temperature, and even the star's speed relative to Earth. To delve deeper, space-based telescopes like the Hubble and newer advancements like the James Webb Space Telescope enable astronomers to observe these spectra without the distorting effects of Earth's atmosphere. In addition to spectra, astronomers analyze the light's intensity and polarization to detect molecules and isotopes, providing clues about atmospheric composition and surface conditions. Remarkably, the Kepler Space Telescope used the transit method, observing the minute dimming of starlight as a planet passed across its host star, to reveal not only the planet's size and orbital dynamics, but also hints about its atmospheric components. Every photon collected serves as a cosmic detective, unfolding stories of distant worlds with precision and wonder that continues to expand our horizons. The birth of a star is a majestic process that unfolds within the huge, cold nurseries of space called molecular clouds or nebulae. These clouds, primarily composed of hydrogen gas, occasionally experience a disturbance, a shock wave from a nearby supernova or the gravitational tug of a passing star that triggers the cloud's collapse under its own gravity. As regions within the cloud become denser, their gravitational pull becomes stronger, causing more material to clump together. This process, known as gravitational contraction, marks the beginning of a protostar, a stellar embryo, so to speak. As the protostar accumulates more mass, it heats up due to the gravitational energy being converted to thermal energy. When the core temperature reaches about 10 million degrees Celsius, nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing an immense amount of energy in the process. This energy creates an outward pressure that counteracts the gravitational collapse, stabilizing the young star and propelling it into the main sequence phase of its life. This balance of gravity pulling inward and thermal pressure pushing outward sustains the star for millions to billions of years, depending on its mass. The ignition of fusion is the celestial equivalent of a birth cry, signaling the arrival of a new star that will shine brightly and perhaps host future planets in its orbit. The life cycle of a star culminates in a dramatic finale that varies depending on its initial mass. For massive stars, those with 8 times or more the mass of our Sun, their death throes are marked by the titanic event known as a supernova. In these gravitational giants, the fusion process continues to forge elements heavier than hydrogen and helium in their cores, forming layers somewhat akin to an onion. Eventually, the core becomes rich in iron, a fusion dead end since iron does not release energy when it fuses. Lacking the outward pressure from fusion, the core succumbs to gravitational collapse in a fraction of a second, creating an implosion that generates extremely high temperatures and pressures. This implosion rebounds off the core, producing an explosive shock wave that rips through the outer layers of the star. The result is a supernova, an event so luminous it can outshine an entire galaxy for a brief period and be visible across vast cosmic distances. The remnants of the exploded material are ejected into space, enriching the interstellar medium with heavy elements like carbon, oxygen, and iron. Elements that become the building blocks for future stars, planets, and potentially life itself. Meanwhile, the core's fate depends on its remaining mass. If it is between 1 and 3 solar masses, it condenses into a neutron star, an incredibly dense object where protons and electrons merge to form neutrons. If the core is even more massive, it collapses further into a black hole, a region of space with gravitational pull so strong that not even light can escape from it. For less massive stars like our Sun, the journey is less cataclysmic but equally fascinating. They expel their outer layers gently to form a planetary nebula, leaving behind a white dwarf, a dense Earth-sized remnant that gradually cools and fades over billions of years. Whether it ends in a supernova or quietly transitions to a white dwarf, every star's death contributes to the cosmic cycle, seeding space with the ingredients for new celestial bodies and continuing the grand narrative of the universe. A neutron star represents one of the universe's most extraordinary remnants of stellar death. When a massive star exhausts its nuclear fuel and undergoes a supernova explosion, its core, left behind, can collapse into one of two exotic endpoints, a neutron star or a black hole, depending primarily on the remaining core mass. If the core's mass is between about 1.5 to 3 times that of our Sun, it becomes a neutron star. These incredibly dense objects are only about 10 miles in diameter, but possess a mass greater than that of our Sun, leading to densities so extreme that a sugar cube-sized amount of neutron star material would weigh billions of tons on Earth. The formation of a neutron star involves the core's gravitational collapse in a supernova. This collapse causes protons and electrons to combine, resulting in a composition almost entirely made of neutrons, hence the name. The neutrons are packed together so tightly that the core's density is comparable to that found in atomic nuclei. Such conditions lead to some mind-bending phenomena. In a neutron star, quantum mechanics and the principles of relativity come to the forefront, giving rise to properties like superfluidity in the core and an immensely strong magnetic field. These fields can be trillions of times stronger than Earth's, creating environments where everyday physical laws are dramatically altered. Neutron stars can further manifest as pulsars if they emit beams of electromagnetic radiation from their magnetic poles. As these stars rotate, sometimes several hundred times per second, the beams sweep across space like the light from a cosmic lighthouse. When these beams are aligned such that they periodically point toward Earth, they create a pulsing effect, hence the name pulsar. This pulsing provides astronomers with a precise cosmic clock, useful in studying everything from the interstellar medium to the fundamentals of space-time itself. Thus, neutron stars, born from the cataclysmic deaths of their progenitor stars, continue to illuminate our understanding of the cosmos well beyond their stellar lifespans. Black holes, among the universe's most enigmatic objects, are born from the catastrophic end of massive stars. When a star of at least 20 times the mass of our Sun reaches the final stages of its life, it undergoes a dramatic supernova explosion. In the core of such a star, nuclear fusion processes eventually cease as iron accumulates. Since iron fusion does not release energy but rather consumes it, the outward pressure that once counteracted gravity disappears, leading the core to collapse under its immense weight. During this core collapse, if the remnant core's mass exceeds roughly 3 times that of the Sun, the condensation continues unfalteringly until it forms a singularity, a point of infinite density where conventional laws of physics break down. This process results in the formation of a stellar mass black hole, characterized by an event horizon, the boundary beyond which nothing, not even light, can escape. The powerful gravitational pull of this event horizon warps space-time to such an extent that time itself slows dramatically as one approaches it, creating some of the most extreme environments in the universe. Initially, the black hole may feed on the remnants of the exploded star, drawing in material from the surrounding space. Occasionally, if the black hole is near another star, it can accrete material from its companion, forming an accretion disk that emits intense X-rays and other forms of radiation as the material spirals inward and heats up. This behavior often makes black holes detectable, despite their invisible nature. Furthermore, the merger of black holes with other black holes or neutron stars can produce gravitational waves, ripples in the fabric of space-time that were first directly detected by the LIGO and Virgo observatories. These discoveries not only confirm theoretical predictions, but also open new windows into understanding the most extreme phenomena in our cosmos. Red giants play a pivotal role in the life cycle of stars and in enriching the cosmos with chemical elements. These luminous bloated stars represent a late stage in stellar evolution for stars with initial masses up to about 8 times that of our Sun. After spending the majority of their lives fusing hydrogen into helium in their cores, stars eventually deplete their hydrogen fuel. With fusion temporarily halting, the core contracts under gravity, heating up until the temperatures are high enough to ignite helium fusion. This new fusion phase produces heavier elements like carbon and oxygen. Meanwhile, the outer layers of the star expand dramatically, causing the surface temperature to drop and giving it a red hue, hence the name red giant. As red giants evolve, they shed a significant portion of their mass through strong stellar winds, contributing vast amounts of material into space. This process is particularly significant because it disperses essential elements like carbon, nitrogen, and oxygen into the interstellar medium, elements that are critical for forming planets and ultimately life. Within the core, layers of fusion zones may pulse and eject more material, forming stunningly beautiful planetary nebulae around the dying star. The remaining core, now a dense white dwarf, slowly cools and fades over billions of years. Beyond their role in chemical enrichment, red giants also serve as cosmic yardsticks. Their predictable brightness allows astronomers to use them as standard candles for measuring astronomical distances, contributing to our understanding of the structure and scale of the universe. Additionally, variable red giants, like the well-known Cepheid variables, have pulsating luminosities that help gauge distances to faraway galaxies, thereby also aiding in the calculation of the Hubble constant and the rate of cosmic expansion. Thus, red giants are not merely ending their own stellar lives, but are vital players in the grander narrative of cosmic evolution, star formation, and the chemical complexity of the universe. Pulsars, which are highly magnetized, rotating neutron stars, emit radiation in a fascinating and dynamic process that has captivated astronomers since their discovery in the 1960s. These cosmic lighthouses are born from the remnants of supernova explosions, leaving behind a core that is dense, rapidly spinning, and possessing an extremely strong magnetic field. The rotation periods of pulsars can range from milliseconds to a few seconds, making them some of the most precise celestial timekeepers known. The emission of radiation from a pulsar is primarily due to its intense magnetic fields, which accelerate charged particles to near the speed of light. As these particles spiral along the magnetic field lines, they emit beams of electromagnetic radiation, including radio waves, X-rays, and gamma rays. The magnetic axis of the pulsar, which is the axis around which these charged particles are channeled, is typically not aligned with the rotational axis. Therefore, as the pulsar spins, the radiation beams sweep across space. If one of these beams crosses Earth, an observer detects a pulse of radiation, hence the name pulsar. Imagine a pulsar as a cosmic version of a lighthouse. The light beam isn't constant, but flashes each time its rotating orientation aligns with our line of sight. The regularity of these pulses is so remarkable that pulsars have been likened to cosmic clocks, with some being precise to within a fraction of a millisecond over years of observation. The exact timing of these pulses can even be used to test the fundamentals of physics, such as general relativity, and to search for gravitational waves. Therefore, the pulses tell not only the story of the pulsar's own workings, but also serve as tools for exploring and understanding the broader cosmos. A white dwarf is the dense stellar remnant of a medium-sized star that has exhausted its nuclear fuel and shed its outer layers. When stars like our Sun run out of hydrogen to fuse in their cores, they undergo a series of transformations, ultimately expanding into red giants. Following this phase, the outer layers are expelled, creating a planetary nebula, while the core, now exposed, becomes a white dwarf. These remnants are typically about the size of Earth, but possess a mass comparable to that of the Sun, resulting in extraordinary densities. 1 teaspoon of white dwarf material would weigh several tons. White dwarfs are characterized by their lack of ongoing nuclear fusion. Instead, they shine due to residual thermal energy left over from their former stellar lives. Over billions of years, these stellar cinders radiate away their stored heat, gradually cooling and dimming. Despite the cooling process, white dwarfs remain stable due to electron degeneracy pressure, a quantum mechanical effect that arises because electrons resist being compressed into the same energy states. This pressure counteracts the force of gravity, preventing the white dwarf from collapsing further. As eons pass, a white dwarf will continue to cool and lose luminosity, theoretically transforming into a black dwarf, a hypothetical stellar remnant that has cooled sufficiently to no longer emit significant heat or light. However, given the age of the universe, no black dwarfs are expected to exist yet, as even the oldest white dwarfs have not had enough time to cool completely. Aside from their gradual cooling, white dwarfs can have dramatic ends if they are part of a binary star system. In such cases, the white dwarf may accumulate material from its companion star, eventually reaching a critical mass known as the Chandrasekhar limit. This can trigger a Type Ia supernova, a colossal explosion that completely obliterates the white dwarf, dispersing its material into space and further enriching the cosmic nursery with heavy elements. In this way, white dwarfs are far from mere stellar fossils. They play active roles in the ongoing cycle of stellar and galactic evolution, providing valuable insights into the fate of stars and the intricate processes that govern our universe. Binary star systems, where two stars orbit a common center of mass, exhibit a rich tapestry of interactions that significantly influence their evolution and properties. The gravitational dance between these stellar companions can lead to phenomena not seen in solitary stars, impacting both their structure and eventual fate. The mutual gravitational forces in a binary system determine the dynamics of the orbit, which can range from nearly circular to highly elliptical, depending on the initial conditions of the system. One of the most compelling influences in binary star systems is mass transfer. In such systems, one star might expand and fill its Roche lobe, a teardrop-shaped region around a star within which material is gravitationally bound to that star. When this happens, material can flow from one star to its companion through what is known as the inner Lagrangian point. This mass transfer can dramatically alter the evolutionary paths of both stars involved. For instance, a star that receives mass can grow substantially, potentially rejuvenating its nuclear fusion processes and extending its life. Conversely, the donor star may be stripped down to a dense core, possibly transforming into a white dwarf, neutron star, or even a black hole, depending on its initial mass. Another phenomenon unique to binary systems is tidal forces, which can induce synchronous rotation. This means that one or both stars rotate at a pace such that the same hemisphere always faces its companion, much like how the Moon is tidally locked with Earth. Over long periods, these tidal interactions can lead to orbital changes, causing the stars to spiral closer together or move apart. In closely bound systems, this can lead to more extreme events, such as stellar mergers, where the two stars coalesce into a single, more massive star, often accompanied by an outburst of energy. Binary interactions also give rise to exotic and dramatic phenomena such as X-ray binaries, where a neutron star or black hole accretes material from a normal companion star, producing intense X-ray emissions. Furthermore, binary systems are crucial for type Ia supernovae, which occur when a white dwarf accumulates enough mass from its companion to trigger a runaway nuclear reaction, leading to a catastrophic explosion. Such supernovae not only serve as standard candles for measuring cosmic distances, but also play a pivotal role in seeding the universe with heavy elements. Through these intricate interactions, binary star systems enrich our understanding of stellar dynamics and the broader processes that shape the universe. Ui Scuti, a gargantuan red supergiant located in the constellation Scutum, holds the distinction of being one of the largest known stars by radius. Situated approximately 9,500 light-years from Earth, Ui Scuti was discovered during a survey of the Milky Way in the mid-20th century. However, its colossal scale became more evident with detailed observations made in subsequent decades. The estimated radius of Ui Scuti is about 1,700 times that of our Sun. To put this in perspective, if Ui Scuti were placed at the center of our solar system, its outer surface would extend beyond the orbit of Jupiter, engulfing the orbits of Mercury, Venus, Earth, Mars, and possibly even the asteroid belt. Despite its vast size, Ui Scuti is not the most massive star. Its mass is somewhat less than that of large stars, like Eta Carinae, measuring between 30 and 40 times the mass of the Sun. The star's low density and extensive atmosphere contribute to its immense volume. Ui Scuti is also characterized by its tremendous luminosity, which is about 340,000 times greater than that of the Sun. This luminosity is a result of both its large surface area and the relatively cooler temperature of its outer layers, around 3,200 Kelvin, which gives it a distinctive red hue. The star exhibits variability in brightness due to pulsations in its outer layers, characteristic of many red supergiants. These pulsations can cause the star's radius to vary slightly over time, contributing to its designation as a semi-regular variable star. The eventual fate of Ui Scuti is as dramatic as its current state. As a red supergiant, it will continue to lose mass through powerful stellar winds and convection-driven ejections. Eventually, it is expected to end its life in a supernova explosion, scattering heavy elements into space and leaving behind either a neutron star or a black hole. Through its life and death, UI Scuti demonstrates the incredible extremes of stellar evolution and the dynamic processes that govern the lives of the universe's most colossal stars. Stellar winds, the continuous flow of charged particles ejected from a star's outer layers, exert a profound influence on the surrounding space. These winds vary significantly, depending on the type of star, ranging from the gentle solar wind produced by our Sun to the powerful outflows from massive stars and evolved giants. In all cases, stellar winds play crucial roles in shaping the interstellar medium, driving galactic evolution, and influencing planetary systems. For stars like our Sun, the solar wind carries away about 1 million tons of material each second. Despite its relative gentleness, this flow of charged particles creates a vast bubble in space known as the heliosphere, which extends far beyond Pluto. The heliosphere acts as a shield, protecting our solar system from much of the interstellar medium's harmful cosmic radiation. When the solar wind interacts with planetary atmospheres, it can strip away atmospheric gases, as seen with Mars, which lost much of its atmosphere due to its weak magnetic field. For Earth, the solar wind's interaction with our planet's magnetic field creates beautiful auroras near the polar regions. In contrast, the winds from massive stars, such as O-type stars and red supergiants, can be millions to billions of times stronger than the solar wind. These winds strip away significant portions of the star's mass over their lifetimes, enriching the interstellar medium with heavy elements and influencing star formation regions. The forceful outflows from these stars can create spectacular nebulae, such as the famous Horsehead Nebula, by compressing and shaping surrounding gas clouds. When massive stars end their lives in supernova explosions, the ejected material, along with the momentum imparted by the stellar winds, seeds the interstellar medium with elements like carbon, oxygen, and iron, essential for the formation of new stars and planets. Furthermore, stellar winds from massive stars can trigger the birth of new stars by compressing nearby gas clouds, a process known as triggered star formation. These winds can also clear out the regions around young stars, dispersing the gas and dust that form planetary systems and influencing the final architecture of those systems. Stellar winds act as both creators and sculptors, driving the cyclical nature of stellar and planetary evolution, and ensuring that the cosmos remains dynamic and ever-changing. In the depths of space, cosmic events and catastrophes shape the universe in dramatic ways. These phenomena offer a glimpse into the powerful forces at work across the cosmos. Each event, from the explosion of massive stars to the collision of entire galaxies, plays a crucial role in the cosmic tapestry. Supernovae are the explosive finales of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes and the outer layers are violently ejected into space, creating a supernova explosion. This event releases an enormous amount of energy, briefly outshining entire galaxies. The explosion enriches the surrounding space with heavy elements like iron and gold, seeding future star systems and contributing to the cosmic cycle of matter and energy. The process begins when nuclear fusion in the core of a massive star ceases, causing the core to collapse under its own gravity. This collapse triggers a shockwave that propels the outer layers into space. The resulting supernova can shine as brightly as 10 billion suns and release more energy in a few weeks than our Sun will in its entire lifetime. The remnants of this explosion, known as supernova remnants, expand outward, creating stunning nebulae and scattering elements across the galaxy. Gamma-ray bursts, some of the most powerful events in the universe, originate from the collapse of massive stars or the merger of neutron stars. These bursts release intense beams of gamma radiation that can travel across billions of light years. If a gamma-ray burst were to occur within our galaxy and its beam were directed at Earth, it could strip away the ozone layer, causing severe damage to the biosphere. Fortunately, such events are rare, and the chances of a direct hit are extremely low. Gamma-ray bursts come in two main types: long-duration bursts, which are associated with the collapse of massive stars, and short-duration bursts, which result from the merger of neutron stars. These events are detected by space-based observatories, which capture the brief but intense flashes of gamma rays. Studying gamma-ray bursts helps astronomers understand the most energetic processes in the universe and the conditions that lead to these extraordinary events. When galaxies collide, a cosmic dance of unimaginable scale unfolds. These collisions can trigger bursts of star formation as gas clouds compress and ignite. Over millions of years, the interacting galaxies merge into a new, larger galaxy, often forming spectacular tidal tales of stars and gas. While individual stars rarely collide due to the vast distances between them, the gravitational interactions can dramatically alter the structure and evolution of the galaxies involved. The Milky Way, our home galaxy, is on a collision course with the Andromeda galaxy. In about 4 billion years, these two giant galaxies will begin to merge, creating a new galaxy, often referred to as Milkomeda or Milkdromeda. During this process, the gravitational forces will reshape both galaxies, potentially triggering new star formation and altering the orbits of existing stars. The resulting galaxy will be a blend of the Milky Way and Andromeda, showcasing the dynamic nature of our universe. Cosmic rays, high-energy particles that travel through space, are detected using instruments on Earth and in space. These particles, originating from supernovae, black holes, and other energetic processes, provide valuable insights into the most violent and energetic events in the universe. By studying cosmic rays, scientists learn about the conditions and processes in distant astrophysical environments, contributing to our understanding of cosmic evolution. Cosmic rays are composed mainly of protons, but they also include heavier atomic nuclei and high-energy electrons. When these particles strike the Earth's atmosphere, they create showers of secondary particles, which can be detected by ground-based observatories. Space missions, such as the Voyager probes and the Alpha Magnetic Spectrometer on the International Space Station, also study cosmic rays, helping to unravel the mysteries of their origins and their role in the universe. The Great Attractor is a massive gravitational anomaly that influences the motion of our galaxy and many others in the region. Situated about 150 million light-years away, its immense gravitational pull affects the large-scale structure of the universe, drawing galaxies toward it. Studying the Great Attractor helps astronomers map the distribution of mass in the universe, revealing hidden structures and dark matter concentrations. The discovery of the Great Attractor was a significant milestone in our understanding of cosmic dynamics. It is part of a larger structure known as the Laniakea supercluster, which encompasses our Milky Way and thousands of other galaxies. The study of such large-scale structures provides insights into the distribution of dark matter, the mysterious substance that makes up about 27% of the universe's mass energy content. Understanding these gravitational anomalies helps astronomers piece together the complex web of interactions that shape the cosmos. Black holes grow through accretion and mergers. Accretion occurs when a black hole pulls in nearby matter, such as gas and stars, forming an accretion disk that spirals inward, heating up and emitting intense radiation. Mergers happen when two black holes collide and merge, releasing gravitational waves that ripple through space-time. These processes significantly impact their host galaxies, influencing star formation and the overall dynamics of the galactic environment. The growth of supermassive black holes, which reside at the centers of most galaxies, is a subject of intense research. These black holes can have masses ranging from millions to billions of times that of our Sun. The interaction between black holes and their surrounding environments can regulate the growth of galaxies by either triggering or quenching star formation. The detection of gravitational waves from black hole mergers by observatories like LIGO and Virgo has opened a new window into the study of these enigmatic objects, providing direct evidence of their existence and behavior. Magnetars are a type of neutron star with an extremely powerful magnetic field. These magnetic fields are so intense that they can distort atoms and generate strong bursts of X-rays and gamma rays. Magnetars can affect nearby space by altering the behavior of particles and magnetic fields, making them fascinating objects of study. Magnetars are thought to form from the remnants of supernovae, where the core of a massive star collapses into an incredibly dense object composed primarily of neutrons. The magnetic fields of magnetars are billions of times stronger than that of Earth. making them the most magnetic objects in the universe. These intense fields can cause starquakes, sudden shifts in the magnetar's crust that release vast amounts of energy. Studying magnetars helps scientists understand the extreme conditions that can exist in the universe and the physical processes that govern their behavior. Cosmic collisions, like those between asteroids and planets, play a crucial role in shaping planetary surfaces and atmospheres. These collisions can create craters, cause volcanic activity, and even contribute to the formation of atmospheres by delivering water and other essential compounds. Understanding these impacts helps scientists piece together the history of our own planet and others in the solar system. The impact of a large asteroid or comet is believed to have caused the mass extinction event that wiped out the dinosaurs 66 million years ago. Such collisions release enormous amounts of energy, generating shockwaves, heat, and debris that can have global consequences. Studying impact craters on Earth, the Moon, and other planetary bodies provides valuable information about the history of our solar system and the frequency of these catastrophic events. Missions like NASA's DART, Double Asteroid Redirection Test, are designed to study and potentially mitigate the threat of future impacts. A nearby supernova could have significant effects on Earth's biosphere. The intense radiation from a supernova could deplete the ozone layer, increasing the amount of harmful ultraviolet radiation reaching the surface. This could lead to widespread ecological disruptions and affect the evolution of life on Earth. However, the likelihood of such an event occurring close enough to impact Earth is very low. The historical record suggests that nearby supernovae may have influenced life on Earth in the past. Evidence from isotopic anomalies in ancient sediments points to the possibility that supernovae explosions could have had ecological impacts. By studying the effects of supernovae on Earth's environment, scientists can better understand the potential risks and the ways in which life on our planet has adapted to cosmic events. Planetary systems can be disrupted by close encounters with other stars. These gravitational interactions can alter the orbits of planets, potentially ejecting them from their systems or causing them to collide with each other. Studying these encounters helps astronomers understand the stability and evolution of planetary systems, including our own solar system. The early history of our solar system was shaped by such gravitational interactions, which influenced the orbits of the planets and the distribution of small bodies like asteroids and comets. Close encounters with other stars can lead to the capture of rogue planets that do not orbit any star. These encounters also provide insights into the dynamics of star clusters, where stars are born and evolve. Understanding these processes helps scientists piece together the history of our solar system and the factors that contribute to the formation and stability of planetary systems. Through the study of cosmic events and catastrophes, we gain a deeper appreciation for the dynamic and ever-changing nature of the universe. These powerful phenomena not only shape the structure and evolution of the cosmos, but also provide critical insights into the forces that govern it. Galaxies, the sprawling islands of stars, gas, dust, and dark matter that populate our universe, come in various forms, each with distinct characteristics and evolutionary histories. The most commonly recognized types of galaxies are spiral, elliptical, and irregular galaxies, with further classifications within each category to account for their diverse structures and features. Spiral galaxies, such as our Milky Way, are characterized by their flat, rotating disks containing stars, gas, and dust, with a central bulge of older stars. These galaxies often feature well-defined arms that spiral outward from the central bulge, tightly wound in some cases and loosely in others. The arms are sites of active star formation, where gas and dust coalesce to give birth to new stars, contributing to the galaxy's bright and vibrant appearance. Spirals are further divided into normal spirals and barred spirals, the latter distinguished by a bar-shaped structure of stars extending from the central bulge before the spiral arms begin. Elliptical galaxies, on the other hand, range from nearly spherical to elongated shapes and are classified by their degree of ellipticity, denoted from E0, nearly spherical, to E7, highly elongated. These galaxies generally contain older stars and have little gas and dust, resulting in minimal star formation. As a result, Elliptical galaxies appear more uniform and less structured than spirals. They are often found in densely populated regions of the universe, such as galaxy clusters, and are believed to have formed through the merger of smaller galaxies, which could explain their varied shapes and sizes. Irregular galaxies defy the ordered structures seen in spiral and elliptical galaxies, appearing chaotic with no distinct shape. These galaxies often contain significant amounts of gas and dust, leading to active star formation. Irregular galaxies may be the result of gravitational interactions or collisions with other galaxies, causing their irregular shape and chaotic appearance. The Large and Small Magellanic Clouds, neighboring galaxies to the Milky Way, are prime examples of irregular galaxies. Additionally, there are lenticular galaxies, which serve as a transitional form between elliptical and spiral galaxies. Lenticular galaxies, or S0 galaxies, have a central bulge and a disc-like structure similar to spiral galaxies but lack well-defined spiral arms. They have a significant amount of old stars like elliptical galaxies and usually little star formation activity, often attributed to the depletion of their gas and dust over time. These varying types of galaxies provide critical insights into the numerous processes involved in galaxy formation and evolution. By studying their structures, compositions, and interactions, astronomers can piece together the complex history of the universe and the dynamic life cycles of galaxies within it. The formation and evolution of galaxies are epic narratives that span billions of years, marked by a succession of dynamic processes influenced by gravity, dark matter, gas dynamics, and cosmic events such as mergers and supernovae. Galaxies are believed to have begun forming relatively shortly after the Big Bang, around 13 billion years ago, from primordial fluctuations in the density of matter in the early universe. Initially, regions with slightly higher densities of dark matter, a mysterious, invisible form of matter that does not emit light but exerts gravitational pull, began to collapse under their gravity, forming the first dark matter halos. These halos attracted baryonic matter, ordinary matter composed of protons, neutrons, and electrons, which cooled and condensed within them, giving birth to the earliest stars. These first-generation stars, often massive and short-lived, quickly exhausted their nuclear fuel, culminating in supernova explosions that enriched the surrounding gas with heavier elements and contributed to the formation of subsequent generations of stars. As these proto-galaxies evolved, they merged and coalesced to form larger structures. The hierarchical model of galaxy formation suggests that small galaxies merged to form larger ones, leading to the diverse population of galaxies we observe today. This merging process can trigger intense periods of star formation, often referred to as starbursts, and significantly reshape the galaxies involved. For instance, the Milky Way is believed to have formed through the accumulation and merger of many smaller protogalaxies. Throughout their lifetimes, galaxies continue to evolve through processes such as accretion of intergalactic gas, interactions with neighboring galaxies, and internal dynamics. Spiral galaxies, for example, maintain their form through the continuous rotation of their disks, with density waves triggering star formation within their spiral arms. Elliptical galaxies, often found in galaxy clusters, may evolve from the merging of spiral galaxies, which can scramble the coherent rotational motion into random orbits, resulting in their elliptical shape and older star population. Moreover, the activity of supermassive black holes at the centers of galaxies can also influence their evolution. These black holes can accrete vast amounts of gas, forming active galactic nuclei, AGN, that emit prodigious amounts of energy, sometimes outshining the entire galaxy. The energy output from AGN can drive powerful winds that expel gas from the galaxy, potentially quenching star formation and contributing to the galaxy's transition into a more passive evolutionary phase, as seen in many elliptical galaxies. Interactions and encounters with other galaxies are also crucial drivers of galactic evolution. Gravitational interactions can stir up galactic structure, leading to the formation of tidal tails, rings, and warps. Major mergers can transform spiral galaxies into elliptical ones, while minor mergers and accretions of smaller satellite galaxies continue to shape their host galaxies. The formation and evolution of galaxies are intricate processes orchestrated by the interplay of gravity, dark matter, gas dynamics, and cosmic events. These processes transform simple initial structures into the complex, diverse galaxies we see today, each telling a story of the universe's ongoing evolution. The Andromeda Galaxy, also known as M31, holds a unique and significant place in our understanding of the universe, serving as a cosmic Rosetta Stone in multiple ways. First and foremost, Andromeda is the closest spiral galaxy to the Milky Way, positioned about 2.5 million light-years away, making it a prime subject for detailed astronomical study. Its proximity allows astronomers to observe and analyze its structure, dynamics, and star population with a level of precision that is not possible for more distant galaxies. One of the most profound aspects of Andromeda is its impending collision with the Milky Way. Current measurements indicate that Andromeda and the Milky Way are on a collision course, set to merge in about 4 to 5 billion years. This future event will dramatically reshape both galaxies, likely resulting in the formation of a massive elliptical galaxy, sometimes referred to as Milkomeda or Milkdromeda. The study of this impending merger provides invaluable insights into galactic dynamics and evolution, as it offers a real-time model for understanding the more common galactic collisions that occur in the universe. Additionally, Andromeda's sheer scale and features illuminate many facets of galaxy formation and evolution. Andromeda is slightly larger than the Milky Way and contains approximately 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. This vast collection of stars includes stellar populations of various ages, providing a comprehensive snapshot of stellar evolution. The galaxy's spiral arms, dust lanes, and halo, composed of globular clusters and satellite galaxies, further enrich our understanding of the structural components that define spiral galaxies. Observations of these features help astronomers refine models of how galaxies form, evolve, and interact over cosmic timescales. Moreover, Andromeda has played a historical role in expanding our conception of the universe. In the early 20th century, the debate on whether spiral nebulae were part of the Milky Way or distant island universes culminated in Edwin Hubble's observations of Andromeda. Hubble identified Cepheid variable stars within the galaxy, using their periodic variability to calculate their distance. His findings proved that Andromeda was far outside the Milky Way, fundamentally altering our understanding by establishing that the universe is populated with countless galaxies, vastly larger than previously imagined. Andromeda continues to be a focal point in cosmology and extragalactic astronomy, as it offers a critical reference for comparing other galaxies and refining our knowledge of universal processes. Whether through its role in future cosmic cataclysms or its contributions to historical and ongoing astronomical discoveries, the Andromeda Galaxy is indispensable in our quest to unravel the mysteries of the universe. Galactic interactions and mergers are cosmic ballets that dramatically transform the involved galaxies, contributing to the dynamic and ever-evolving nature of the universe. These interactions are driven primarily by gravitational forces and can range from gentle tidal influences to violent collisions that blend and reshape entire galaxies. In the early stages of interaction, galaxies begin to feel each other's gravitational pull long before they collide. This gravitational attraction can lead to tidal forces, stretching and distorting the galaxies into elongated shapes. These tidal forces often create long streams of stars and gas, known as tidal tails, which extend far into space. An example is the famous antennae galaxies, where such tails are prominently visible, showcasing the dynamic interplay of merging galaxies. As galaxies draw closer, their mutual attraction can induce several changes. Gas clouds within the galaxies often collide, compressing and triggering bursts of star formation, a phenomenon known as starburst activity. The centers of the colliding galaxies, typically housing supermassive black holes, may also be driven toward each other, eventually merging and coalescing into a single, more massive black hole. The final stage, the actual merging of galaxies, can take hundreds of millions to billions of years. The cores of the galaxies spiral inward, and their stellar populations mix. As the galaxies merge, their shapes can be dramatically altered. Spiral galaxies, with their structured arms, may transform into more amorphous elliptical galaxies as the ordered rotation is disrupted and converted into random orbits. The merging process can also fling stars out into intergalactic space, forming faint but extensive stellar halos around the resultant galaxy. These merger events are not just destructive, they also provide the raw materials for future evolutionary stages of the new galaxy. Gas and dust from the progenitor galaxies can contribute to new rounds of star formation long after the merger has coalesced. The gravitational forces at play can also channel gas toward the center of the galaxy, potentially feeding the central black hole and triggering phenomena like active galactic nuclei or quasars. Our own Milky Way is not immune to these cosmic encounters. It is currently interacting with the Sagittarius dwarf spheroidal galaxy, a smaller satellite galaxy being gradually torn apart and absorbed. Eventually, in about 4 to 5 billion years, the Milky Way is expected to merge with the Andromeda galaxy, creating a large elliptical galaxy. Through these interactions, the material and stars involved are redistributed, and new galactic structures are formed, enriching the interstellar medium and forging new generations of stars. Galactic interactions and mergers are fundamental processes that drive the evolution of galaxies, shaping their structure, star formation activity, and even the formation of black holes. Studying these events allows astronomers to understand better the life cycles of galaxies and the dynamic processes that govern their transformations over cosmic timescales. The mesmerizing spiral arms of galaxies like the Milky Way can be attributed to density waves, essentially gravitational perturbations that move through the galactic disk. Unlike a solid structure, these density waves compress gas and dust as they move, creating regions ripe for star formation. Picture these waves as cosmic traffic jams. As they travel, they trigger stellar nurseries within the galactic disk. The bright young stars that result form illuminated patches tracing the wave's path and giving rise to the spiral patterns we observe. Interestingly, these arms are not permanent fixtures but are transient. As older stars drift out of these denser regions, they fade into less defined areas of the galaxy. The spiral pattern is continually renewed by new waves moving through the galaxy. The interaction of gravitational forces, including those from dark matter, influences the stability and longevity of these density waves, contributing to the dynamic and breathtaking spiral structures that captivate astronomers and casual stargazers alike. At the center of most galaxies lies a region known as the galactic core or nucleus, a place of extraordinary phenomena and intense gravitational pull. This core often hosts a supermassive black hole, an astronomical entity whose mass can span from millions to billions of times that of our Sun. The supermassive black hole is surrounded by a dense concentration of stars, gas, and dust, all swirling in a chaotic dance influenced by the black hole's immense gravity. These black holes can often be detected by observing the rapid orbital motions of nearby stars or from the energy emitted as material falls into them. The galactic core is also a cauldron of energetic processes. In some galactic cores, particularly those of active galaxies, material rapidly accretes onto the supermassive black hole, forming an accretion disk that heats up due to friction and gravitational forces, emitting copious amounts of radiation and sometimes even jetting out streams of high-energy particles into space. This can lead to phenomena such as quasars or blazars, which are among the most luminous and energetic entities in the universe. The radiation and powerful winds from these activities can influence star formation across the galaxy, either triggering new stars to form or blowing away material that could condense into stars, thus playing a crucial role in the evolution of the galaxy itself. Measuring the mass of a galaxy is a daunting yet fascinating endeavor, often requiring the use of several indirect methods. One fundamental technique involves analyzing the rotational curves of galaxies. By observing how stars and gas rotate around the galactic center, particularly in the outer regions of the galaxy, astronomers can infer the distribution of mass. According to the laws of physics, specifically Newtonian mechanics, faster rotational speeds at greater distances from the center suggest the presence of unseen dark matter. This mysterious substance doesn't emit light, but exerts gravitational forces, contributing significantly to the galaxy's total mass. Another method leverages gravitational lensing, a consequence of Einstein's theory of general relativity. When a massive galaxy or galaxy cluster lies between us and a more distant object, it bends the light from the background object, creating distortions or even multiple images known as Einstein rings. By analyzing these distortions, astronomers can estimate the total mass of the foreground galaxy or cluster, including both visible and dark matter. Additionally, measurements of the velocity dispersions of stars and gas within a galaxy, particularly in the central regions, can provide insights into the mass contained within that space. These methods, often used in combination, give us a comprehensive understanding of galaxy mass, revealing a universe far richer and more complex than what we can see with our eyes alone. Dark matter and dark energy, though invisible and elusive, play pivotal roles in the structure and evolution of galaxies and the universe as a whole. Dark matter, which makes up about 85% of the total mass of the universe, acts as the cosmic scaffold upon which galaxies are built. It does not emit or interact with electromagnetic radiation like ordinary matter, making it undetectable by traditional telescopes. Instead, its presence is inferred through its gravitational effects. Within galaxies, dark matter forms a sprawling, spherical halo that envelops the visible components. This halo ensures that galaxies hold together, providing the necessary gravitational glue to sustain their structural integrity. On a grander scale, dark energy, which constitutes approximately 70% of the universe's energy content, is even more enigmatic. It is thought to be responsible for the accelerated expansion of the universe, a discovery that shook the foundations of cosmology in the late 20th century. Dark energy's repulsive force counteracts gravity on cosmic scales, influencing how galaxies cluster and how the large-scale structure of the universe evolves over billions of years. While dark matter dictates the formation and stability of galaxies, dark energy determines the fate of the universe itself, stretching the fabric of space-time and driving galaxies apart at an ever-increasing rate. These two components, dark matter and dark energy, though unseen, are the silent architects of the cosmos, shaping the universe in profound and mysterious ways. Star clusters form within galaxies through the gravitational collapse of giant molecular clouds, immense regions of cold gas and dust that exist throughout the galactic disk. These clouds can span several light-years and contain enough material to give birth to thousands of stars. The process begins when some perturbation, such as a nearby supernova explosion or the tidal forces from a passing star, triggers parts of the cloud to collapse under their own gravity. As the cloud contracts, it fragments into smaller clumps, each of which can collapse further to form individual stars. The newly formed stars within these clusters are usually bound together by their mutual gravitational attraction. There are two primary types of star clusters: open clusters and globular clusters. Open clusters, like the Pleiades, are relatively young and contain a few hundred to a few thousand loosely bound stars. They are often found in the spiral arms of galaxies where star formation is most active. Globular clusters, on the other hand, are much older and more tightly bound, containing hundreds of thousands to millions of stars. These clusters reside in the halo of the galaxy and provide valuable insights into the early stages of galactic evolution. The stars in these clusters often exhibit similar ages and compositions, offering a unique look into the conditions that prevailed when they formed. Thus, star clusters serve as both active breeding grounds for new stars and ancient relics that illuminate the history of their host galaxies. Observing distant galaxies opens a window into the early universe, allowing astronomers to peer back in time and understand the processes that shaped the cosmos. Because light from these galaxies takes billions of years to reach us, we see them as they were long ago, effectively observing different epochs of cosmic history. By studying the formation and evolution of galaxies at various distances, astronomers can unravel the sequence of events that led to the complex and structured universe we inhabit today. This includes insights into the initial stages of galaxy formation, star formation rates over cosmic time, and the role of mergers and interactions in galactic evolution. In addition, distant galaxies provide valuable clues about the nature and behavior of dark matter and dark energy. By mapping the distribution and movements of these far-off galaxies, astronomers can infer the influence of dark matter on large-scale structures and understand how dark energy drives the accelerated expansion of the universe. Observations of phenomena such as quasars, which are extremely luminous and often found in the early universe, also help illuminate the conditions around supermassive black holes during their most active phases. By piecing together data from distant galaxies, Scientists can construct detailed models of cosmic evolution, helping us understand not only the distant past, but also the future trajectory of our universe. Rockets overcome Earth's gravity through the principles of Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. To launch a rocket into space, it must generate a force greater than the gravitational pull exerted by Earth. This is achieved by expelling high-speed jets of gas in the opposite direction from the rocket's intended path, creating thrust that propels the rocket upward. The process begins with the combustion of rocket fuel in a combustion chamber. This fuel can be either solid or liquid, though liquid fuels provide more precise control and efficiency. When the fuel combusts, it produces hot gases that expand rapidly and are funneled through a nozzle at the base of the rocket. The nozzle directs the gases downward, creating an upward thrust. The force of the ejected gases generates the necessary upward acceleration to counteract and eventually overcome the downward force of gravity. The amount of thrust required depends on the rocket's mass and the gravitational force it needs to overcome, quantified by the rocket equation. The equation highlights the importance of the rocket's velocity and the efficiency of its propulsion system, typically enhanced using multiple stages. Each stage jettisons after expelling its fuel, reducing the rocket's mass and allowing the remaining stages to accelerate more efficiently. By continuously expelling fuel and shedding stages, rockets incrementally build up the necessary velocity to escape Earth's gravitational influence, reaching the speeds needed for orbit or interplanetary travel. Ion drives, also known as ion thrusters, are a type of propulsion system that offers significant advantages over traditional chemical rockets, particularly for long-duration space missions. Unlike chemical rockets that rely on the rapid combustion of fuel to generate thrust, ion drives use electric fields to accelerate ions to incredibly high speeds, producing a steady and efficient thrust over extended periods. The operation of an ion drive begins with the ionization of a propellant, typically a noble gas like xenon. In the ionization chamber, electrons are stripped from the xenon atoms using either an electron impact or a process known as electron bombardment. This creates positively charged ions. These ions are then directed towards a pair of charged grids situated at the back of the drive. The first grid is positively charged, attracting the ions, while the second grid is negatively charged, repelling them. The electric field between these grids accelerates the ions to speeds up to 90,000 miles per hour, after which they exit the thruster, creating a gentle but continuous thrust. One of the key advantages of ion drives is their fuel efficiency, or specific impulse, which is far greater than that of conventional chemical rockets. This high specific impulse means that ion drives can operate for much longer periods, making them ideal for deep space missions where carrying large amounts of chemical propellant would be impractical. The trade-off, however, is that ion drives produce much lower thrust levels compared to chemical rockets, resulting in longer times to achieve the desired velocity. Despite this, ion drives have successfully been used in various space missions, such as NASA's Deep Space One and the Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres. These missions demonstrated the viability of ion propulsion for intricate, long-duration expeditions, marking a significant milestone in space exploration technology. By offering a way to maximize fuel efficiency and operational longevity, ion drives represent a promising path forward for the next generation of interplanetary travel and exploration. Navigating the vast distances of space is a formidable challenge that requires precise planning, sophisticated technology, and continuous adjustments. Space probes rely on a combination of onboard systems and ground-based support to chart their courses through the cosmos. The process begins with accurate trajectory planning, leveraging gravitational assists, and utilizing precise propulsion systems for course corrections. One of the fundamental tools for space navigation is the Deep Space Network, DSN, a global array of ground-based antennas managed by NASA. The DSN communicates with spacecraft, transmitting commands and receiving data. By carefully timing how long it takes for signals to travel between Earth and the probe, engineers can determine the probe's distance and position. This method, known as radio tracking, is coupled with Doppler shift measurements to assess the spacecraft's velocity. The Doppler effect shifts the frequency of the signals received from the spacecraft, providing information about its speed and direction relative to Earth. In addition to ground-based navigation, probes are equipped with star trackers and gyroscopes for autonomous navigation. Star trackers use cameras to capture images of star fields, comparing them to a built-in star catalog to determine the probe's orientation in space. Gyroscopes measure changes in the spacecraft's orientation, helping maintain a stable trajectory. Together, these tools enable the probe to know its position and orientation accurately. Key to navigating vast distances are also gravitational assists, a technique where a spacecraft flies close to a planet or moon to gain speed and alter its trajectory using the celestial body's gravity. This maneuver allows probes to reach distant destinations with less fuel. For example, the Voyager missions utilized multiple gravitational assists to explore the outer planets and now travel towards interstellar space. Navigating space also requires on-the-fly adjustments. Engineers use small thrusters to make mid-course corrections, ensuring the probe stays on its intended path. These adjustments are calculated based on continuous monitoring and data analysis, allowing the probe to make the necessary tweaks to its trajectory. Through the interplay of ground-based communication, on-board navigation systems, and the ingenious use of gravitational forces, space probes can traverse the vast distances of the solar system and beyond, bringing humanity closer to understanding the profound mysteries of the universe. Satellite technology plays an indispensable role in modern society, profoundly impacting various aspects of our daily lives, scientific endeavors, and global communication. One of the most visible impacts of satellite technology is in communication. Satellites enable instant worldwide connectivity, allowing television broadcasts, internet services, and phone calls to reach even the most remote corners of the Earth. They form the backbone of the global communication infrastructure, enabling everything from live sports broadcasts to emergency services coordination. Satellites are also critical in weather forecasting and environmental monitoring. Weather satellites provide real-time data on atmospheric conditions, helping meteorologists predict weather patterns and track severe storms, hurricanes, and other natural disasters. This information is crucial for early warning systems, which save lives and minimize property damage by allowing timely evacuations and preparations. Additionally, environmental monitoring satellites track changes in the Earth's climate, deforestation rates, ocean temperatures, and polar ice coverage, contributing to a better understanding of climate change and its effects. Navigation is another area where satellite technology has revolutionized our lives. The Global Positioning System, GPS, relies on a constellation of satellites to provide precise location and timing information. GPS technology is integral to numerous applications, including aviation, maritime navigation, logistics, agriculture, and even everyday activities like driving and hiking. The agricultural sector, for example, uses GPS for precision farming, improving crop yields by enabling efficient planting, fertilizing, and harvesting. Moreover, scientific research has greatly benefited from satellite technology. Satellites like the Hubble Space Telescope have expanded our understanding of the universe by providing unprecedented views of distant galaxies, stars, and planets. Earth observation satellites contribute to geology, oceanography, and environmental science, offering invaluable data on the Earth's systems and processes. These satellites enable scientists to study natural phenomena on a global scale, leading to advancements in our knowledge of the Earth and beyond. Lastly, satellites enhance global security and disaster management. They play a crucial role in national defense by providing surveillance, reconnaissance, and secure communication channels. Disaster response efforts leverage satellite imagery to assess damage, coordinate relief operations, and monitor recovery progress. Satellite technology is integral to the modern world, underpinning communication, navigation, environmental monitoring, scientific research, and security. Its impact spans from everyday conveniences to critical applications that safeguard and improve our way of life. Communicating with distant spacecraft involves a sophisticated combination of technologies and techniques designed to ensure that data can be transmitted across the vast expanses of space. The cornerstone of this communication effort is the Deep Space Network, DSN, which is managed by NASA. The DSN consists of 3 large antenna complexes strategically located around the world, in California, Spain, and Australia. This global distribution ensures continuous contact with spacecraft as the Earth rotates, covering nearly the entire sky at all times. The communication process begins with spacecraft equipped with transmitters and receivers that send and receive radio signals. These signals carry scientific data, telemetry, information about the spacecraft's status and health, and commands from mission control. The spacecraft's high-gain antenna focuses the radio waves into a narrow, powerful beam directed toward Earth, optimizing the signal's strength. As the signals travel through space, they weaken, so receiving them requires highly sensitive ground-based antennas. When the DSN's massive parabolic antennas receive the weak signals from the spacecraft, they amplify and convert them into electronic data that can be analyzed. The process is reciprocal. Mission Control uses the DSN to send commands to the spacecraft, instructing it to perform specific maneuvers or tasks. These commands are transmitted as radio signals, which the spacecraft's receiver decodes and executes. Because of the immense distances involved, often spanning billions of miles, there is a significant time delay in communication. For instance, messages to or from a probe near Mars can take around 20 minutes each way, while signals to far-flung spacecraft like those in the Voyager program can take over 18 hours to reach their destination. This delay necessitates precise planning and autonomy. Spacecraft often have onboard systems capable of making critical real-time decisions without waiting for instructions from Earth. Moreover, modern communication strategies sometimes employ advanced techniques like phased array antennas, which can steer radio beams electronically without moving parts, and low-gain antennas that offer broader coverage but less power. Data compression algorithms are also used to maximize the efficient use of limited bandwidth, ensuring that every bit of valuable scientific information is transmitted effectively. Communicating with distant spacecraft relies on a global network of sophisticated ground-based antennas, powerful transmitters, and sensitive receivers. The use of advanced technologies and careful planning allows for the precise control and data retrieval essential for the success of deep space missions, continually pushing the boundaries of our exploration and understanding of the cosmos. Space elevators are an intriguing concept envisioned as a more efficient and cost-effective way to send materials and potentially people into space compared to traditional rocket launches. The basic idea involves a long cable or tether extending from Earth's surface to a point beyond geostationary orbit, approximately 35,786 kilometers, 22,236 miles above the equator. By attaching a counterweight at the tether's end in space and anchoring the other end to the Earth, the centrifugal force due to Earth's rotation would keep the tether taut. Elevators, or climbers, would travel along this tether, transporting cargo and passengers to and from space. The concept of a space elevator eliminates the need for rockets to overcome Earth's gravity, dramatically reducing the energy and cost associated with launching payloads into orbit. Additionally, it offers the potential for continuous, safer, and more environmentally friendly access to space, facilitating tasks like satellite deployment, space station resupply, and even space tourism. However, the feasibility of space elevators faces several significant challenges, primarily related to the materials required to construct such an extensive and robust tether. The tether must be exceptionally strong and light to support its weight and the tension caused by the centrifugal force from Earth's rotation. Currently, no known material possesses the necessary mechanical properties to construct a space elevator tether. Carbon nanotubes and graphene are often cited as potential candidates due to their remarkable strength and lightness, but manufacturing these materials at the required scale and maturity remains a substantial hurdle. Additionally, the engineering and logistical challenges are immense. The construction would require precise coordination and would be an unprecedented technical endeavor. Issues such as atmospheric conditions, including weather and lightning strikes, space debris, and the Earth's rotation dynamics, pose further complications. The climbers themselves would need to be powered efficiently, possibly through wireless energy transfer methods like laser beaming or by carrying energy sources. Despite these challenges, research and theoretical studies continue to explore the feasibility of space elevators. experimental advancements in materials science, particularly in nanotechnology, might one day make the concept more practical. Organizations such as NASA and various private enterprises have expressed interest in the potential of space elevators, contributing to the ongoing investigation and development. In conclusion, while space elevators remain a captivating vision for the future of space travel, significant scientific and engineering breakthroughs are required to make them a reality. The concept holds promise for revolutionizing access to space, but substantial challenges must be overcome before space elevators can transition from science fiction to science fact. Artificial intelligence, AI, is increasingly becoming a cornerstone of modern space exploration, offering powerful tools to enhance the efficiency, safety, and capabilities of missions. Scientists employ AI in various aspects, from mission planning and spacecraft operation to data analysis and autonomous systems. One significant application of AI is in mission planning and navigation. AI algorithms can optimize spacecraft trajectories, making efficient use of fuel and time. For instance, NASA's Mars rovers Curiosity and Perseverance use AI to plan their routes across the Martian surface, selecting paths that maximize scientific yield while avoiding obstacles. This autonomous navigation allows rovers to cover more ground and conduct more complex missions without relying on real-time instructions from Earth, which can be delayed by up to 24 minutes due to the distance. In spacecraft operation, AI contributes to the automation of routine tasks and decision-making processes. Spacecraft equipped with AI can perform diagnostics, detect anomalies, and execute corrective actions without waiting for instructions from mission control. This capability is crucial for deep space missions, where communication delays can hinder timely responses. AI systems like the European Space Agency's ESA Autonomous Sciencecraft Experiment use onboard AI to prioritize and process scientific data, allowing the spacecraft to make immediate observations and decisions based on mission objectives. Data analysis is another critical area where AI shines. Space missions generate enormous amounts of data, including images, spectra, and telemetry. AI-powered tools can quickly process and analyze this data, identifying patterns and anomalies that might be missed by human analysts. For example, AI algorithms are used to sift through vast datasets from telescopes, identifying new celestial objects such as asteroids and exoplanets. These algorithms can recognize subtle signals within data, accelerating discoveries and enabling scientists to focus on high-priority targets. AI also plays a role in robotic systems designed for space exploration. Robotic arms and manipulators used on spacecraft and space stations can benefit from AI to perform complex tasks like repairing equipment, assembling structures, or conducting scientific experiments. These robots, equipped with machine learning capabilities, can adapt to new tasks and environments, improving their versatility and reliability. In addition to these applications, AI is essential for future missions involving human astronauts. AI can support life support systems, monitor astronauts' health, and provide assistance in emergency situations. Virtual assistants, similar to AI-based personal assistants used on Earth, can help astronauts manage their schedules, access information, and troubleshoot problems. Artificial intelligence enhances the capability and efficiency of space missions in numerous ways. By automating tasks, optimizing trajectories, analyzing vast datasets, and providing autonomous decision-making, AI empowers scientists and engineers to push the boundaries of space exploration, unlocking new frontiers and paving the way for the next generation of discoveries. The latest advancements in spacesuits, often referred to as extravehicular mobility units, EMUs, reflect significant technological innovations aimed at enhancing astronauts' safety, mobility, and comfort while performing extravehicular activities, EVAs, in the harsh environment of space. These developments are driven by the needs of future deep space missions, such as NASA's Artemis program to return to the Moon and eventual missions to Mars. Here are some of the key advancements. One major area of focus is the improvement of mobility and flexibility. Traditional spacesuits, like the ones used during the Apollo missions or on the International Space Station, ISS, are bulky and restrict astronauts' movements. New designs, such as NASA's XEMU, Exploration Extravehicular Mobility Unit, feature enhanced joints and materials that provide greater flexibility, allowing astronauts to move more naturally. These suits incorporate advanced bearings and redesigned joints to facilitate movements like bending, kneeling, and walking, which are essential for tasks on the lunar or Martian surface. Another significant advancement is life support and environmental control. Modern spacesuits include more sophisticated systems to regulate temperature, pressure, and humidity, ensuring that astronauts remain comfortable and safe in varying conditions. Advanced thermal control systems help manage the extreme temperatures experienced in space, ranging from -250°F in the shadowed regions to +250°F in direct sunlight. The XEMU, for instance, features a more efficient portable life support system, PLSS, that provides improved cooling and removes carbon dioxide more effectively, increasing the duration and safety of EVAs. Suit materials have also seen considerable innovation. New fabric technologies provide better protection against micrometeoroids and space debris while remaining lightweight and durable. Additionally, new materials help improve thermal insulation and resistance to radiation. Some modern suits are designed to be modular, allowing for easier replacement and upgrades of individual components, which is crucial for long-duration missions where resupply opportunities are limited. Heads-up displays, HUDs, and augmented reality, AR, are being integrated to give astronauts real-time data and enhanced situational awareness. These systems can project information such as suit status, navigation, and mission objectives directly onto the helmet visor, reducing the need to look at handheld checklists or instruments. This hands-free access to information can increase efficiency and reduce the cognitive load on astronauts during complex tasks. Additionally, advanced communication systems are being incorporated to facilitate better interaction between astronauts and mission control. Enhanced audio systems with noise-cancelling capabilities ensure clear communication even in the noisy environments of spacecraft or space habitats. Lastly, efforts are underway to design spacesuits that can be quickly and easily donned and doffed, addressing challenges associated with the more cumbersome donning process of traditional suits. Quick entry features and adjustable sizing options make these suits more user-friendly and adaptable to astronauts of different sizes, enhancing overall mission readiness and efficiency. These advancements collectively aim to make spacesuits lighter, more flexible, and more durable while ensuring the safety and well-being of astronauts as they explore new frontiers. As research and development continue, these innovations will play a pivotal role in enabling humanity's return to the Moon, our journey to Mars, and the continued exploration of space. Generating power in space is a critical aspect of ensuring the successful operation of spacecraft, satellites, and space habitats. The primary methods for generating power in space are solar power, nuclear power, and fuel cells, each with its own set of advantages and applications. Solar power is the most common method for generating electricity in space, especially for satellites and spacecraft within the inner solar system where sunlight is abundant. Solar panels made from photovoltaic cells convert sunlight directly into electricity. These cells are often made of silicon or more advanced materials like gallium arsenide, which have higher efficiency rates. The International Space Station, ISS, for example, uses expansive solar arrays to generate power, with each array capable of producing about 30 kilowatts of electricity on average. The energy harnessed from the solar panels is used to power onboard systems and is stored in batteries for use when the spacecraft is in the shadow of the Earth or other celestial bodies, ensuring a continuous power supply. For missions where sunlight is not readily available, such as deep space missions beyond the asteroid belt or those requiring continuous power through long periods of darkness, nuclear power becomes an essential option. Radioisotope thermoelectric generators, RTGs, are commonly used for this purpose. RTGs generate power by converting heat from the natural radioactive decay of isotopes like plutonium-238 into electricity using thermocouples. Notable missions that rely on RTGs include the Voyager probes, the Cassini spacecraft, and the Mars rovers Curiosity and Perseverance. RTGs provide a reliable and long-lasting power source, crucial for missions where solar energy is insufficient. Fuel cells are another technology employed to generate power in space, particularly for shorter missions or when high power output is needed for specific periods. Fuel cells create electricity through a chemical reaction between hydrogen and oxygen, producing water as a byproduct. This method was famously used in the Apollo missions and continues to be employed in modern spacecraft. Fuel cells offer a compact and efficient power source, but are limited by the availability of fuel. Recent advancements and research in space power generation also explore alternative methods and improvements. For instance, scientists are looking into more efficient solar cell materials and the possibility of space-based solar power systems, where solar collectors in space could beam energy down to Earth via microwaves or lasers. Innovative concepts like dynamic solar power systems that track the sun's movement to maximize exposure are also under development. Generating power in space involves a variety of technologies tailored to specific mission requirements. Solar panels offer clean and renewable energy for missions within the inner solar system. RTGs provide reliable power for deep space and long-duration missions, and fuel cells deliver high-power output for short-term needs. Collectively, these methods ensure that spacecraft, satellites, and future space habitats have the electricity required to perform a wide range of scientific, exploratory, and operational tasks in the challenging environment of space. 3D printers are increasingly playing a transformative role in space missions, offering numerous benefits that enhance the efficiency, flexibility, and sustainability of space exploration. The ability to manufacture parts and tools directly in space, rather than relying solely on supplies brought from Earth, represents a significant advancement for long-duration missions and deep space exploration. One of the primary roles of 3D printing in space is the manufacturing of replacement parts and tools. Space missions, especially those far from Earth, face the challenge of limited storage and cargo capacity. By using 3D printers, astronauts can fabricate necessary components on demand, reducing the need for a comprehensive inventory of spare parts. For instance, the International Space Station, ISS, has successfully utilized 3D printing to create various tools and parts. In 2014, NASA's Zero-G printer, developed by Made in Space, printed its first object on the ISS, demonstrating the feasibility of additive manufacturing in microgravity. This capability allows crew members to address unexpected repairs and maintenance tasks efficiently, without waiting for resupply missions. Another critical benefit of 3D printing is the potential for in-situ resource utilization, ISRU, during planetary missions. For future missions to the Moon, Mars, or other celestial bodies, 3D printers could use local materials to construct habitats, tools, and other infrastructure. For example, lunar regolith, the Moon's surface material, can be utilized as a raw material for 3D printing. This reduces the amount of material that needs to be transported from Earth, significantly cutting down mission costs and increasing self-sufficiency. 3D printing also enables the production of complex and customized components that would be challenging or impossible to manufacture using traditional methods. This capability is particularly valuable for creating lightweight structures with intricate geometries that optimize strength and material usage, crucial for spacecraft and habitat design where weight and durability are critical considerations. NASA and other space agencies are exploring advanced 3D printing techniques, such as metal additive manufacturing, to produce high-performance parts for rockets and spacecraft. In addition, 3D printing supports scientific research and experimentation in space. Researchers can design and print specialized equipment and experimental setups tailored to the unique conditions of their studies. This flexibility accelerates scientific progress by allowing rapid prototyping and iteration of research tools directly in space, without the long lead times associated with sending equipment from Earth. Furthermore, 3D printing has health and safety applications. The ability to print customized medical devices such as splints, braces, or even biocompatible materials for medical treatments ensures that astronauts have access to essential healthcare supplies during extended missions. This capability can enhance crew safety and well-being, providing immediate solutions to medical emergencies or health issues. Overall, 3D printing is poised to revolutionize space missions by providing on-demand manufacturing, enabling the use of local resources, allowing for the creation of complex and efficient structures, and supporting scientific and medical needs. As the technology continues to advance, its role in space exploration will only grow, contributing to more sustainable, resilient, and versatile space missions.